for it.
Well, good morning, good afternoon, good day, wherever you may be, because I know we have folks from Australia to the West Coast of the US, to the East Coast, to Europe. So first of all, thank you to everyone that's participating in all the odd time zones and using this new technology that's actually allowing us to have these kinds of conversations. As much as we'd like to be in person, this is really kind of cool that we're able to get everyone engaged like this across the country. So this is absolutely fantastic. For those of you who do not know me, I'm Dan Dumbacher, the Executive Director for AIAA. And Ken and Madhu asked me to do a little intro, and I was more than happy to do it because it's always fun to work with the Los Angeles, Las Vegas section, and particularly on a topic that's near and dear to my heart. I come to AIAA, for those of you who do not know, after 33 years at NASA, starting off on shuttle before STS-1 and then ending up as the Deputy AA for Exploration Systems until I went to go teach at some university in Indiana with an engineering school in 2014. And then AIAA called. So what you guys what the conversations today are extremely, extremely important. As we look as a species to, as I say it, extend the human neighborhood to low Earth orbit and even beyond, and extend the human neighborhood to the moon and to eventually to deep space, the kind of forward thinking that this architecture, thinking ahead, be creative, is really help setting the stage for what the future will look like and how we can best serve society in general and the human species. So I find that these kinds of discussions are very, very engaging and very, very important, because if you don't know what you're aiming for, it's kind of hard to get there. And we keep, at AIAA, we're working hard to, as we say in the Ascend world, we talk in terms of building our off-world future, and that's what this is all about. And so I just don't want to take a lot of time, because you guys have some great stuff to go talk, and you don't need to hear from me. But I just want to say, again, thank you to everyone for participating, everyone around the globe on this topic. To some people that might seem a little far out, but we need that target. We need to know where we're aiming for, and you guys are helping define what that is. And also congratulations to Ken and Madhu and the entire LA Las Vegas section for pulling all of this together. You have quite a series of speakers here, and it's rather impressive. And I'm looking forward to hearing from you guys and seeing what kind of visions you have, because I just want to know where we're going to go and how we're going to get there and what it looks like. And the sooner we get there, the better. So Madhu, I'll turn it over to you, and looking forward to the discussion. Thank you.
Thank you, Dan. Okay, it's so nice to have Dan come in and open the session for us. All I had to do was send in a little note and said, "Hey, Dan, look at our program. Would you like to join us?" And boy, oh boy, he gave me a happy thumbs up, and I'm so glad you're with us, Dan. AIAA is very special, and it's done so many things for the community. It's done so many things for me. I used to be the education chair, Dan, some years ago. Do you remember Bob Brodsky? Yeah, he was my my mentor in many ways. And then Eberhard Rechten, the one who started the systems architecting program at USC. He was my mentor. And he used to tell me stories from the aerospace days and how we got the DSN running. And so when we have Australians on board, they need to know we have contacts there. We've done some magical things right there in your home country. Now I'm going to go share my screen. Yes, everybody remembers Bob Brodsky. Can give me a minute. Ken, what do you see on the screen now?
It's still your face.
Oh, okay.
I try the green button.
I'm not on the green button, wait. Now what do you see?
Still your face.
Still my face, okay, good. Yeah, I gotta see.
Oh, it's coming up.
Good.
Great.
Okay, we are 2 minutes ahead of schedule, but I'm going to run because usually I'm accused of running late on my slides. So welcome all to this wonderful program. I give all the credit to Ken, and thank you to Dan for opening the event. So happy that people are joining us. I teach some crazy classes in the School of Engineering and in the School of Architecture. My education and training are in both fields. Welcome all. This is the third session of the Space Architecture Group. It's international because people have dreams all over the world. And I'm glad some of you are here. So the moon and Mars is waiting for architects. Before I start, I must mention that USC has a very unique angle on astronautics. It's a very specific program. We also have an aerospace engineering program. So once you fly out the bounds of Earth and into space, our astronautical engineers come to play. Neil Armstrong landed on the moon while he was doing the mission. He was assigned to the moon mission while he was doing his master's here at USC. And the story is that the dean asked him what his difficulty was. He told him he had a mission to the moon. The dean, without even flinching, said, "No problems, just bring back the report and you'll be fine." So that's how the story goes. Now, the program has grown. It's growing every year. So within this program is my studio. It's called the ASTE 527 studio. And we are focused only on one thing alone. Can you imagine? Can you dream? Can you bring something to me at the end of the term? I don't care what the agency or the industry thinks. I want your mind. Can you do that for me? And you know what? Every single time we have ideas, and we don't really care whether it goes with this person's idea, this agency's idea, the expert's idea. No, we want them to think originally, and it helps them. It's all about imagination and creativity. This is my class, and we have some very special friends. Hello, Lapa. We've got a few people watching in too. I think you all know this man from the t-shirt he's wearing. Buzz said he will tune in today. If he comes in, Ken, give him a minute. But we have a wonderful class. Now, in the architecture school, which happens to be the other semester that I teach, they ask some damned hard questions. They want to know, what are we doing for humanity? A lot of us are thinking, most of us are thinking how to keep people alive in space, in the extraterrestrial surfaces, and how to do this in a responsible and safety critical manner. We come back home and talk to the architects. They're impressed, but they want to know, what are we doing to help the billions of people on planet Earth? So between the two, I get quite a few questions, and we have a great discussion. Architects want to know questions about how space architecture can impact life on Earth. This is our textbook. It's a timeless book. The first edition appeared before the turn of the century, the second edition in 2007, and we are going to do the third edition. We are working on it. It should be out next year. And we call it timeless because every time there is news in the papers, the magazines, the trade journals, and the literature, we go back in our book and say, somebody is thinking about it. So it's a great book. Buzz Aldrin wrote the foreword, and I hope Buzz is tuned in. He's a national hero, and he's a champion for human space flight. He has a new initiative called the Human Space Flight Institute that we are all pushing for. He wants all the universities to come together and compete with designs and collaborate in finally selected ideas. He wants the whole world to do that. I don't have to mention that space architecture involves engineering and architecture and all imaginable professions. I've met people, artists, I've met lawyers, doctors, some of them sit in our studio. Now, what is space architecture about? It's about habitats in space for people to live in. It is alien, as you can see. We are looking at Apollo 17 image here, I think. Yes, and that is probably Harrison Schmitt, who took that picture, is looking out and seeing the lunar surface. No, this is the Apollo 11 picture. That's right. Anyhow, it's highly interdisciplinary. And I want you to look at our archives, for those who have not yet, to see what we do. It's been around for a long time. And we started curating it only in 1999. I remember starting it in early 1990. And we do a lot of interesting things and we talk about it. And every time NASA comes up with a new idea, it's already somewhere in here, including the title and the moniker and everything. So take a look at it. I love to draw. Anybody who says they are a space architect and can't take a pen and put it down on paper quickly, they're not a space architect. Sorry, buddies, learn to draw. So I drew these things, and when I first did it before a bunch of engineers, they all shocked themselves and said, that guy in the corner is doing something really out of this world. He's crazy. But you know what? It went on to become my work, graduated me, and we went on to think about something that is coming of age now. The idea that we can build massive things in orbit around the Earth. Space station is already there, and now we think, because of all the satellites going up, we have to be careful with this environment. These are parts from my work, and now we think we can build these things using the space station. Why not? And here you see our lunar craft about to land on the moon. Students in the class talk about orbiting space stations, different kinds of orbiting moon stations, and we think it's already happening. The Earth orbit is the next entry for any nation that wants to have an immediate impact on what we are going to do next. So I welcome all the space architects to be thinking about what to do in Earth orbit to extend us to the moon and Mars and beyond. We talk about ideas about putting sampling surfaces and shooting samples into orbit where they can be picked up. The Moon Village Association is a new idea. Somebody will talk about it. I think the Vice President is with us. Their first payload is already being studied. And the idea is to put a telescope on the moon, looking back to Earth 24/7, and let all the people of the Earth look at how beautiful, how fragile planet Earth is. Our team talks about going back to the moon, going back to the Apollo site and examining Apollo, and also looking at the scientific aspects of things like the skylight that you see here. It's called the Tranquillitatis Pit. We think about rovers. We think about building structures using robots on the moon. This is a project that was done at USC. You will hear more about it today, about constructing shelters using robots. Ideas that have originated at USC, and the professor is with us today. I'm so happy. You will hear more about it. Landing pads are important. We talk about that. My own favorite thing is to send thousands of people to the moon for a holiday, to let them take a train and go around and see how beautiful planet Earth is looking from what Buzz Aldrin calls the grand desolation. Planetary defense could use structures on the moon. Here you see a high-power laser shooting down meteorites coming not only to impact Earth, but also to hit places, exposed assets on the moon. We're going to put telescopes, we're going to put habitats, and they all need to be protected. Here you see a laser doing the job for us. My own thinking is that we should get all the nations together, put up structures on the moon so they can visit, spend some time, come back, have a beer garden party, and there's no reason why we should not brag about looking up at the skies and say, you know, it's fantastic to fly from here to here, take a train from here to here, and see all the beautiful structures on the moon. We have people looking at doing Olympics on the moon, sporting activities. I sent this to, I believe, the Clinton administration to suggest that the presidential library should have a spot on the moon. And President Clinton wrote me a handwritten letter. That brings us to today's event, which is, thank you, Dan. Am I on time? Guess, oh gosh, oh, I'm sorry about this. Okay, we are ready to go on to Professor Sandra Meusburger. Ken?
Yes.
Are you with us?
Yeah, Sandra is here.
Okay, you should have stopped me. Go for it. We are ready for the next.
Oh, yeah.
We want to catch up, but Ken, I was hoping you would stop me. Okay, good.
Good timing, don't worry. She's here, so I just asked her to start a video. Yeah, she's here.
Hello, shall I share my screen?
Yeah, go ahead.
Thank you. All right. Can you see it?
Yes.
Great. So, good evening or good morning, whatever, where are you coming from? Thank you for this invitation. And today I would also thank you for showing your book, Madhu. I have to say that your book, The Moon, was one of the most favorite books when I started to work on space architecture. It's really timeless. I love it. So today I would like to present some recent research that it's just being published on my site. Many of you know that I have worked in habitability research with the focus on the relationship between space and humans for many years, also myself now. So as architects, we all know how important habitability is. In space so far, unfortunately, it was seen as nice to have. But as space architects, we know it will be vital for mission success, especially in the near future, when more and more people will travel to more and more places. So habitability and its integration to design is also an important topic in the work with my students. Unfortunately, the Springer books are not freely accessible, but all the space architecture projects from our studio is. So I invite you to look at this link and look at the projects from the studio. I'm talking today about my latest endeavor. The last 4 years, I had the great pleasure to work closely with the space psychologist, Dr. Sharon Bishop. Together, we share a common passion on the relationship about space and humans. And both of us have approached this from different angles. So Cheryl has always been hunting for the answer to the questions, what constitutes the best fit person to live happily in extraterrestrial environments? And I myself have been chasing after what constitutes the best fit space to live happily in extraterrestrial environments. And the past 4 years, through a lot of discussions, we have come up with a real synergetic achievement towards the design of living spaces in extreme environments. And I would like to give you a little insight to this research now. In 1963, the authors of the paper Habitability in Space Stations started with the question, what does habitability mean? And further, but what does it really mean? So, interestingly, support and evidence for the need of habitability integration today can be found in every decade. So one large part of the research and the book is to lay open the various and also varying concepts of habitability. Habitability is an umbrella term. It is for a concept that has evolved over time. It has evolved from habitability as location to habitability as living space today or in the future. It is used by different professions with a variety of underlying foci. And Cheryl and me have been arguing that the habitability model shall be centered around the inhabitant in experience of space as central core. As such, habitability describes the suitability and value of a built habitat for its inhabitants in a specific environment over time. Together, we trace this evolution from space to place in history, and we give examples from relevant research. It is clear that today there is no perfect analog for extraterrestrial habitats. This is because each isolated and confined environment has its own strengths, but also its own limitations. So knowledge transfer from one environment to the other has been tricky and is even sometimes not a good idea. So how are we to evaluate and prove effectiveness of habitation factors when we lack true analogs for extraterrestrial conditions? The space station Skylab is a good historical example for learning of an environment we don't know about. It is by experience. Its long duration missions and large open volume provided for the very first time the opportunity to learn about movement in microgravity. We have to remember that the first study on the neutral body position comes from these 3 missions. And when we say that we can say that Skylab was the first testbed in space, the first analog, the first experimental space station. It featured a number of innovative and experimental designs: a deployable shower, private crew quarters, a toilet mounted on the wall, and man involved in keeping the house clean and tidy was also not commonly seen at that time. Some things worked and some did not. A lot of restraints, for example, that the Skylab astronauts experimented with are not used anymore. And also there was a big fight on the inclusion of the large wardroom window by Raymond Levy. It was actually closed most of the time because there was nothing to see. The windows in the multi-docking adapter proved to be of much better use because they provided a 360-degree view. In addition to experiencing, how can we approach habitability design integration from a scientific point of view? Well, given the premise that extraterrestrial environments share a core set of limiting characteristics and human habitation in such places share common challenges like isolation, confinement, and restricted access to others, Cheryl and me started to look at the commonalities across the experiences people made in ISIS and their habitats. And this makes the second main part of our research, a review of studies and the architecture of habitability missions. As our research is a co-project, combining on the one hand side the psychology of a person living in extreme environment, and on the other side the socio-spatial dynamics of the group living in extreme environments, we choose examples from missions that involve living over a period of time in a habitat that serves as protection from extreme environment. We did not include expeditions or camps, otherwise it would help to explain the concept. So this is the group we're looking at, and for the presentation of the floor plans and sections that we show and that we compared, we're using a color code that is aligned to human activities to make identification and comparison easier. So the first group is Chamber Research Facilities. Initially, experimental research on habitability factors was conducted in these highly controlled habitats, laboratories or capsule research. The Moscow Institute of Biomedical Problems has had an isolation facility in operation already since 1967. However, the most famous one is the most recent one, Mars 500, a 520-day mission in 2011. Overall, chamber research facilities are full-scale habitats with the control of laboratory conditions. They lack true risk and isolation, conducted in the safety of larger facilities, but despite of, they have been critical testbeds for technology and process development and validation. In situ research facilities, overall, the use of them has provided a bridge between the overly controlled laboratory and capsule habitats with all the extraneous controlled elements and the conditions of the real environment. So they provide greater risk and also provide greater demands for crew autonomy. And of course, not to forget the experience from the real space environment. A number of habitability studies and experiences from astronauts, cosmonauts, and taikonauts serve today as a resource for detailing future habitation. But still, so far, most of the know-how and experience comes from low Earth orbit. So, can we build the perfect habitat? All existing habitats and many of the concepts even envisioned for the near future, we have to say, are impoverished places to live in. We really have to realize that as soon as the perspective shifts to long-term missions, further away from Earth, less than ideal conditions will not be viable anymore. Complicate matters even further. Many of the Earth's inherent natural conditions must be provided through technology. But some of these sub-conditions may not be viable alternatives for the entirety of conditions that they seek to mimic. So, for example, does a picture of a forest on the wall adequately compensate for never interacting with actual plants? Therefore, we thought it is critical to first identify if and which factors related to our natural conditions are needed for human well-being. And then, if so, what are the characteristics and dimensions of those that need to be surrogated? And finally, which technologies and socio-spatial strategies are available to do so? You will notice here that the first two questions are most important. For any proposed solution to a problem and proposed design, it is of great importance to understand the underlying socio-spatial relation. Only then we think it is possible to come up with a solution that deserves the name habitability design solution. The good news is here that there is not just one possible solution to a problem, but a myriad. And we can make use of this large pool of ideas. So in the concluding work that Cheryl and me did, we have summarized major overarching habitability issues in relation to their underlying socio-spatial relationships. One example is the principle of, we all know of, making the most of all resources. But the fact that it will be a considerable span of time before we have communities in the size, let's say, of McMurdo of Earth, the negative impact of limited group size will be with us. In literature and science, it has been shown that team members in longer missions spend less social time together than during shorter missions. So the implications from the trends for a space architect have direct impact on the design. For instance, the propensity to spend less social time together as duration increases means we need to provide the capability to create more social space to limit social distances over time, and at the same time provide more private space to meet growing psychology needs. So, living with others is not easy. We all have experienced that in the best of circumstances. But remove the opportunity to get away in a small space and limit the opportunity to interact with others. The simple act of being alone becomes a huge challenge in an ice habitat. Little interpersonal difficulties can become big problems. The design of such a habitat shall take this inevitability of interpersonal conflicts into account. So there would be preventive measures, such as we clearly define personal spaces and the ability to have control over it. And there would be mitigation measures, such as opportunities for social engagement, sports and leisure. Design features could address multiple needs. To plan for multiple routes throughout base, include modification possibilities depending on different needs, and function allocation of activities, for example, a typical design task for a space architect. Another example is to understand the psychological dynamics of living in a small and confined space. The psychological experience of too little volume, for example, is associated with feelings of crowdedness. The interesting part here is that this is not only a question of the actual size of the space. So feelings of crowding are also related to visual complexity and extreme artificiality. One important aspect is to include the life cycle of a habitat, and during the design process, all space modules have looked efficient and spacious, as can be seen in the left picture, on the top right picture, and yet all of them have turned into cluttered spaces without exception. And this is even valued for simulation facilities on Earth. Other impacts to be integrated include visual complexity and spatial perception. So I would like to conclude with a statement by Dr. Weiss, a psychologist with relevant work on spatial habitability. He said, it's not how large you make it, it's how you make it large. And I thank you very much for your attention and again for the invitation. Thank you, Madhu.
Thank you so much, Sandra. That is a beautiful introduction to today's events. You know, we will take questions in the end, Sandra, and you know, I want you all to be using the chat room. I think Ken will be monitoring it. I will be too, and we'll have dialogues in between. Thank you so much. What a beautiful beginning. Thank you. Our next speaker is Vittorio. And Vittorio is coming to us from, I think from Italy, or from, are you here in the US now, Vittorio?
I'm always a bit everywhere. In this moment, I'm in Europe, but lately I'm based in Houston.
Okay.
Yeah.
Great, go for it.
Okay. Thank you, Madhu, for the invitation, first of all, and thank you, Sandra, for your beautiful presentation. I share my screen. I have to, Sandra, I think that you have to stop sharing before I can start sharing. Okay. I hope, can you see my screen, right?
Yes, we can.
Okay, thank you, everybody. Today I will talk about a research that it's more than a single research. It's like a group of research that lately characterized my basically my research focus, and is the human-robot collaboration as an enabler for a scalable human presence in space. A research that I started at CIXA in Houston at the Sasakawa International Center of Space Architecture. So I'll try to be fast because I have a lot of things to say. But when I started my journey in space architecture, I had a really clear idea what space architecture was. And now after 5 years, I'm not so sure again. Because I got to know all the different aspects that space architects they need to address in their projects, and so space architects they need to be a bit engineers, a bit robotic experts, and planetary scientists, and astronomers, and many other things. So it's really difficult sometimes to understand what really space architecture is. So I think that it's up to us to define it and define the way in which we decide to impact the space architecture field. So I'm currently, just to present very briefly myself, I have a bachelor and a master in architecture from UAB in Venice. And after I'm finishing my master in space architecture at CIXA in Houston, but I already started a PhD in aerospace engineering and science at the Politecnico di Bari. At the same time, I worked as a consultant for Search last year on the Project Olympus, and I currently project manager of Vector Robotics, that is like a drone company, and I'm a registered system engineer at Incus. This is just like a part of the things that actually make my professional lives. So my vision that I developed during these years is that really to enable like a large-scale application for human space exploration, we really need to focus on automation because automation it's a great enabler for a safe and accessible space environment. In the way that we discovered from the 60s to today that robots and AI they can really make our job easier and safer when it comes to a so harsh environment like space or a planetary surface in the heliosphere. So I decided to focus a lot my research on this topic that I find very fascinating. And of course, this involves a lot of the study of what is space robotics. Why space robotics is so important? Well, first of all, I found a very interesting paper of J.B. Garvin that was in the directorate of space exploration at NASA in the 90s, that he talked about the different skill sets that human and robots they demonstrate in space. Of course, this can be considered a bit out of date right now because we are talking about the 2005 and many things changed in this last 15 years. But he basically, together with the GPL, they investigated this aspect. So, and they took a certain set of skills that you can see here, and they tried to understand how this, how much they were effective, humans versus robots, in this skill set. Well, as you can see, robots are basically worse than human, but almost everything. But they have three specific things that they are very good at. The first is the precision, and we know how important precision is in space. The second is detection, and it's basically connected to the idea that robots can identify problem way faster than humans, and also this expands to the artificial intelligence. And the third thing is probably the most important, the expandability. When we lose a probe or a robot, we are not losing a human life. And this is extremely important for us because we all care about our lives. And even if we really like to explore ourselves, the new things, we want to do it in a safe way. So I asked myself, why if there is this big division between these skills, why don't do both at the same time? And so I started working a lot on the concept of cooperation between human and robot in space exploration. And this, I think, it's a great tool for then planning of next human missions. And in which I already see from the next NASA ESA programs how robotics is now incorporated in these programs in a very broad way. And so I want to, in this presentation, I want to present briefly three projects of mine that I developed during these years that they make use of this concept of human-robotic collaboration and partnership. So I start from the low Earth orbit to go farther and farther. The first concept that I always liked is the concept of robotic augmented EVA. That means that humans are very good, as we said before, at certain things like dexterity or even like to respond to unknowns and unforeseen situations. While robots are, they ensure a very high repeatability in certain tasks. So my idea is that the spacesuits are a great instrument for EVA because without, we will have no way apart from pure robotics to interact with the spacecrafts. But the spacesuits are very limiting in terms of human skills. The EVAs are are limiting for the dexterity, the strength of humans, and also they are potentially dangerous for many aspects of the human body. So I wanted to design an asset that could make instead stronger these skills. Instead, so the idea is that instead of having a spacesuit that limit human skills, I wanted a spacesuit that instead could enhance human skills. From that, it started a project that it was the MMEVR, that stands for Multi-Mission Extravehicular Robot. And it's basically that. It's like it's a multi-limb space robot that it's present both capabilities like of navigation through RCS, so through vectorial movement, like the NASA MMU, but at the same time it uses highly precise manipulation capability, like for example the Canadair, and that we saw it in autonomous mode, and here we see it in cooperative mode with an astronaut. So the robot can act standalone, but at the same way can operate in a cooperative way with an astronaut in EVA. Of course, like this concept, in a certain way, comes from something that we already did in space. That was the MMU. The MMU is, I think, it was an incredible invention, and has been left behind just for certain logistic and usability problems. But we used it and we success in different space mission. Here we see it through the in a photo. This is a photo of the SMM retrieval in 1984, in which the MMU was used as a way to intercept and as like a mobile platform to interact with big satellites. So my system, it made use of basically, it's composed by 2 robots, a service module that is attached virtually to any spacecraft thanks to the International Docking Port standard, and a control station for the robotic limbs inside the spacecraft. So the robotic limbs are not operated by the astronaut, but they are operated by another crew member inside the station. And this is, we see the 3 different system components because the robot it's modular and it can be used in different configuration based on what is the task that's needed to be produced. This is like the robot module, and it uses reaction wheels to achieve like a very precise orientation, and as these 2 limbs that can interact with the different tools. We will see after how. This is the navigation module. This is the one that provides basically the MMU capabilities, so the vectorial navigation. There are basically 2 N2 tanks that together with the reaction will offer an autonomy of basically 3-4 hours. And there is an harness through which, like the robot is docked to the backpack of the astronaut. Here also we can see the different tools that I designed that can interact with the limbs, and we have 2 grippers, like an adhesive clamp that is used to retrieve satellites, for example, an high density laser that is derived from the space shuttle program, and basically it's a laser printer to retain, for example, small debris holes. So how it works? The service module it's attached to any spacecraft, as I said before, through a SpaceX Dragon XL. It works as a giant multi-purpose airlock, and what it does is like deploy the robots in space. As you can see here, and it uses its limbs and reaction wheel to dock itself and to assemble autonomously in space. After that, it can be used again both in autonomous mode in augmented mode. From the inside, is controlled through an optic exoskeleton that is weared by the crew member inside, and they will control 2 arms every time. So the astronaut inside can decide which of the 2 arms can be controlled, while the other 2 can be controlled by an AI that will learn during the first missions from the astronauts. Well, during this track of the development of this project, I went through the whole thing. It has been very fascinating as a process. I did modeling, printing, and testing of a 1:1 scale model of the robots, and that is currently under testing using immersive technologies like virtual reality. This is it's not the last production state of the robots. There are more. It's a more advanced situation, but yeah, to just let you understand. And at the same time, we designed and built immersive simulations to test the robot in 1:1 scale. This is like the simulation environment in which we are testing the robot through basically 2 different missions in which the robot will be used to exchange some external components of the lunar gateway. Second project, I have to be very fast, but yes. The second project is basically it's a lunar robotic rover that has been awarded as finalist project for the Rascal NASA competition last year. The rover has obviously used based on an assumption from the LLV program of the Apollo. This is the rover. The rover is completely modular, and it works on the concept that it can be field stripped. So, for example, if the astronaut has a problem, like a leg is broken, they can exchange components in real time to accomplish the mission. But not only, the rover comes in a robotic configuration. So as you can see here, it's come without a command post. So it can perform the first part of this mission autonomously. After, when the astronauts they come on the surface, they basically swap the artificial the computer modules with the control post, so the rover from completely autonomous it become human operated. And here you can see that thanks to its modularity, it can be rearranged during the different phases of the mission for different purposes, like transport or exploration or science missions. Yeah, there was some specific of the rover, like the robotic operated legs, and the concept of having a modular payload box. The third one, and it's very short. It's like my PhD research. My PhD research is based on the robotic construction for Moon and Mars, and we are currently developing at the Polytechnic di Bari like an infrastructure to operate multiple robots at the same time for construction of a single element. So it's like collaborative robotics that it's made through multiple robots printer. It's the whole process. You use a lot of AI algorithm, because the robot, they have to decide autonomously. They have to understand autonomously where they are and how to collaborate with the construction process. To do that, we will use very basic industrial robots on which we will mount a printer head, and each printer head will be basically fueled with regolith simulant cement in form of geopolymer. And I think that was it. Just in time, a bit over, but.
Thank you so much, Vittorio. It's a great lead-in to our next speaker. We will have questions for you about cobots and swarms. But then now we are on to Professor Berok Khoshnevis, who will really take this on because he is the pioneer in several areas of robotic construction. Welcome to Berok. Berok, are you here?
Yeah, he's here.
Oh, great. Okay, go for it. Good morning, Berok. Oh, turn on your mic. Great.
Can you hear me now?
Yes, you can. How are things in Marina del Rey? Are you there or elsewhere?
Yes, I'm in Marina del Rey.
Oh, good to see you.
Thank you. I'm trying to find the share screen on this thing.
Okay, it's a little tricky. Look for the green button on the bottom.
I know, but I click on the Zoom icon.
Ken may be able to help
That
you.
bar doesn't come up.
Okay, let's see if Ken can help you.
Yeah, if you move the mouse to the bottom, see the menu, that should have a green button called Share Screen.
Yeah, I know that. I use Zoom every day.
Oh, okay, sorry.
But it is showing the program on the screen. Yeah, I am sorry. I cannot see the menu of Zoom. The icon is at the lower taskbar, but when I press it, the Zoom menu doesn't pop up.
It could be on the top, depending on your.
All right, if you see shared screen, but then it doesn't come up, maybe we have to give him different permissions because that happens a lot in my class. Sorry to butt in.
No, I don't see the share screen.
You don't see shared screen at the bottom?
No.
Everyone is given the same permission, though.
Okay.
The previous speaker can show.
Where earlier I saw that just a few minutes ago, 5 minutes ago, I saw it, but right now it disappeared.
Yeah, another possibility, you can email to Madhu or email to me. We can show it for you.
Well, it's
maybe you can revoke the permission and then assign again the permission. Probably that will solve.
No, that was assigned to everyone. There's no individual change.
maybe I should
solve it, guys. Give him a minute. Berok will solve it.
maybe I should get out and
come back in. Okay.
Get back into the Zoom again.
Try that.
Sorry about this.
I hope all of you are. Oh, I see John. John has come in. Good morning, John.
Good morning.
Good morning.
Good morning.
I think Berok signed off, just trying to sign back in.
Okay, good. Again, one more time to all of you who are watching. We are just getting started, and those who tuned in right now, we are about to watch literally the history of
It's coming up.
robotic building activities. I was privileged to be part of Professor Khoshnevis' team, and we were surprised that NASA pulled us in again and again to hear more. I hope we delivered. With that, Berok, you're on the air.
I apologize for the delay. Okay, so I have a presentation on the research that I did for NASA over a few years. And as Madhu mentioned, I had the pleasure of having him as a research partner. So this had to do with planetary construction and in-space fabrication. I'm a professor at the University of Southern California and the CEO of a company called Contour Crafting Corporation. Okay, so I have been in the field of 3D printing for a long time. I was there with the pioneers, and I have several inventions in polymeric, metallic, and ceramic. And of course, right now, I'm involved in composite, like concrete, for large-scale 3D printing. I've developed several technologies, the SIS technology, 3D printing of metallic parts has been licensed to HP. And contour crafting has been my flagship technology. And it has advanced to a point where we have different models of the machine now built at the company that I established in 2017. We have made many demonstrations over the years. It's been 25 years now, actually, since I thought about it. And what we aspire to do in the future is to add other activities, other tasks of constructions, because 3D printing only builds the shell of the building. There's still a lot to be done to complete the building. Many different demonstrations we've made, many different technologies we have developed. And we have looked at the infrastructure such as columns, building like large towers, tall towers for wind turbine, and the like. This chart was published in Europe. It shows that contour crafting was truly a pioneering technology, now at least 10 years ahead of its time of other people. So the project with NASA concerned building vertical and horizontal structures. For the vertical structures, we consider two different methods. For the moon situation, we considered the smelting the regolith and extruding it. It was a difficult part of the project. We made some progress, and the effort there was to deal with the brittlety of the extruded. The compressive strength is very high, nearly 40,000 PSI when we melt and extrude the regolith, but the result is just like a glass, it is very brittle. So then for shady areas of the moon and Martian situation, we looked at sulfur concrete. So if you take sulfur and sand and mix them together and heat them, you can actually bond the particles of sand. So then if you could extrude this, you can build objects much like what you do with other paste material or hydraulic concrete on Earth. But the problem is the abrasive nature of the lunar sand, especially. It is extremely difficult to push it through any kind of conduit. So we had to develop a number of solutions, and we used the strong piezoelectric vibration at different stages of this extrusion. And we finally managed to get the thing done. We used an industrial robot to make our demonstrations. What you see here is the sulfur concrete coming out of the nozzle in real time. This is the real speed. And you see the specimens that we have built on the right. Right, this is a 3-layer specimen here. And we have built different structures and at different scales, just for demonstration. The compressive strength of these structures is about 3,000 to 4,000 psi on Earth, which is equivalent of more than 20,000 psi on the moon, and more than 12,000 psi on Mars, because of the lower gravity of those planets. Yeah, so the system that we conceived was based on a robotic arm that we conceived, and the rover that you see is called Athlete, is what's developed at JPL, Jet Propulsion Laboratory. Yeah, so this was just our conception. This technology won the 2014 NASA Grand Prize in international competition. Next were horizontal structures, and at the time we were asked to focus on landing pads. Reality is that so far on these on the moon and Mars, the landing has been done on just soft soil, and the exhaust plume pushes the soil away, and the bedrock is not horizontal. If it is a slant, there's a chance of the lander tipping over. We were told that you cannot use a monolithic structure because of the differential in expansion under heat of the exhaust plume. Therefore, it's best to be made with interlocking tiles. And for that, I actually came up with a new 3D printing concept, which would be actually using a simple rover. And the concept is pretty straightforward. We define, you just have the, on a flat ground, you, if the dust is there, you can start right there. If you have to spread it, you do so. And then you're going to use this kind of rover to define the tiles. Here, for simplicity, the tiles are just square. And the definition is made by depositing inside the soil, the regolith, a higher temperature material, a material with higher melting point. In this case, magnesium oxide. Magnesium oxide is plentiful. The moon and Mars, and the melting temperature is much higher, over 2000 versus about 1100 for the regular regolith. Of course, the lowest melting point ingredient of the regolith is 1100 C melting point, and if that melts, it can fuse the other, so it can act like a binder, like cement or like sulfur. The challenge is just to separate these things, how to keep them separate so that they're mobile with respect to each other. And this is the approach, as I said. We put a insert higher temperature powder there, and that is followed by a magnetron with microwave power. Those lower temperature stuff are melted. These are some samples that we built. This is, of course, a small scale. On the top left, what you see is basically, this is lunar regolith, inside of which we delivered magnesium oxide through a very thin nozzle. It's like a hypodermic needle in a way, which has got a slot on the side. And yeah, and then we put it in sintering furnace. This is microwave sintering. And as you see, these tiles come out pretty accurately, and they're very, very strong. So the idea is that for future landers to not face such a situation. And as you see here, there are more elaborate interlocking tiles that we have conceived. Yeah. So the technology I named SSS, Selective Separation Shaping. And I found out that it is so capable that we can do metallic 3D printing at mesoscale and so on. So we then extended the operation to this approach for metallic, and we did things with bronze and stainless steel. And the nice thing about this technology is that it can build without powder layering. You know, all metallic technologies, powder-based technologies require powder layering, which is not possible in microgravity. But SSS can actually build the stuff without layering, and you can see the surface quality is really comparable or better than selective laser sintering or electron beam machining. And this technology also won a grand prize in 2016. Yes, so we now have a company, Contour Crafting, established in El Segundo, California, and we aspire to get active also again in the space research and development. Thank you, and again, I apologize for the delay.
Thank you so much, Berok. Good to see you looking happy with that beautiful painting in the background. We will ask some questions later on, Berok, but please stay on. Don't run away on your sailboat. We want you here.
Okay, when is the question and answer going to be?
The question and answer will be, I'm afraid it will be at the end of the program, I think. Yeah, but if there is a gap, it may happen sooner, depending on how much time the presentation.
The end of the program is 2 o'clock, right?
It'll be about 3, I think, by the end.
No, unfortunately, I apologize. I really have a big commitment today.
Okay, okay. Thank you so much.
Thank you.
Good to see progress at Contour Crafting Corporation.
Thank you so much. I appreciate it.
Okay, we are on to our next speaker, and it's none other than John Mankins. And John will introduce some of the wonderful things he's working on with the Moon Village Association and other projects. John?
Good morning. It's a real pleasure to be here, and wonderful to follow such an engaging discussion of the progress at Contour Crafting. Just fabulous. May I share screen?
Please do.
So for those of you who may remember a past talk that I gave here at the AIAA group, it had to do with activities by the Moon Village Association, architectural Concepts and Considerations Working Group, of which I am the co-chair with Professor Inotani, formerly with ISAS in Japan. We are conducting last year and this year an international design reference architecture for the Moon Village concept, based on the idea of establishing the first human settlement on the moon by 2045. And we had a workshop online, which Madhu and I and Professor Inotani all co-organized last December. And I have Madhu, it's okay if I talk for about an hour, hour and a half?
I'm afraid I would love to hear you, but you got to stick to your time, John.
Well, maybe I'll just share a few of the, I'll hit the tops of a few of the waves, not even all of the tops of all of the waves.
That'll be good. And then we'll have our discussion over barbecue at Nipomo later.
Very good, very good. So let me ask, seriously, about 10 minutes?
10 minutes is perfect.
Okay, very good. So I won't go to the history. The Moon Village Association would welcome you if you'd like to join. We're very inexpensive, about 10% of an AIAA membership.
I agree.
The Moon Village Architecture Working Group works in the framework of a series of scenarios of alternative futures. These have been updated in the last few weeks from the version that was created initially in 2018. These scenarios are building on the global exploration roadmap, which has been established by the International Space Exploration Coordination Group. It essentially looks at alternative futures, but we are focusing, as I said, on this case study in which we would target a lunar settlement at the south pole of the moon with a variety of operational zones, including the often illuminated south polar lunar ridge, the permanently shadowed regions in the vicinity of that ridge line, the far side of the moon, low lunar orbit, cislunar space, and Earth orbit for other supporting operations. Fundamental assumption is that the advent of very low cost launch is going over the next 6 or 7 years to change everything in cislunar space. This has not quite happened yet, but you see the piece parts like the Falcon 9 reusable, the electric propulsion module that goes with the lunar gateway, and the high power thrusters, high efficiency thrusters of Buzek, the developments of a variety of new systems to take technologies to the moon, demonstrate them, and so on, and the advent of very low cost megawatt solar power in low Earth orbit through these mega constellations. If you haven't thought about it in these terms, let me just say that they're manufacturing at SpaceX approximately 120 Starlink satellites per month. That is very roughly 500 or 600 kilowatts of space solar power every month. So 4 times the International Space Station's power capability every month. This kind of mass production is going to be, I think, a game changer for energy in the inner solar system, particularly in cislunar space, and will make possible the kinds of ambitious development of lunar resources that we were just talking about, and including the manufacture of fuels and so on, because without power, nothing else is possible. I'm going to skip a lot of this material of having to do with the precursors to the location selection and just jump straight to that. Number one issue, being near the sun, having access to the cold traps and the volatiles, and access to them on the surface. So this whole question of surface roughness, the slopes and so on, is extraordinarily critical if you're going to have industrial operations at the lunar poles. A variety of other issues associated with the settlement, having to do with air, water, recycling, the recycling of all of the major chemical cycles, oxygen, carbon, the nitrogen, and so on, and just a host of other issues. One of the number one premises of having a true settlement is that a settlement will have children. It will have settlers, people who live there essentially indefinitely. And there will also be people who are visiting. We anticipate that there will be visitors. And in fact, the first mission of the SpaceX Starship, which they are building, is a space tourism mission. So making this one of the premises, a requirement for a lunar settlement, we think is obvious. I won't talk too much about about a lot of this, because again, I just want to skim through it. The idea is more than one area for habitation. We have not yet gotten into any real detail having to do with the architecture of that habitation. However, the most important consideration is embodied in this picture of the data set from the Lunar Reconnaissance Orbiter LOLA data, the Lunar Orbiter Laser Altimeter data, and in particular that the variation between the highest point in this depiction of the data set and the lowest point is 5 kilometers, and that you have variations of 5 kilometers over distances on the order of 4 kilometers. And so you can have extraordinarily steep and rugged terrain everywhere where there is an interest, where there is an opportunity to develop lunar resources. So everything that's been talked about, we're going to build on these beautiful flat surfaces. Architecture can start out, with this pristine plain that looks a little bit like where Apollo 11 landed. All of that is, in my opinion, crazy and will never happen, because the things that are of interest, the energy that we need, the sunlight that we need, and the permanently shadowed regions where the ice is located that we are going to try to develop, the reason why everyone is going to the moon, these are separated by 5 kilometers, 8 kilometers, 12 kilometers in linear distance, and by 2, 3, 4, 5 kilometers in elevation. And in between, you have an extremely rugged terrain with variations of 50, 100, 200 meters over lengths the size of a soccer field. And so these are non-trivial. They're very interesting slopes. There are some fairly benign areas. One of these, which we have chosen for the site of the habitation system, this first lunar settlement, which, by the way, I might mention, we are naming Oasis, the off-Earth autonomous settlement in Selene, where Selene is the name of the moon. So it spells Oasis. Oasis 1 will be here in this crater, which is on the far edge of the ridgeline away from Shackleton. This is one of the largely illuminated regions. This is an elevation map taken from the LRO data by shaving out of the online data set a terrain map at individual elevations separated by about 20 meters each. And this is a 3D model that I constructed just to show visually what these look like. And the core idea is for this first human settlement to be here in this upper crater on the outer edge of this the South Polar Ridge, and that in the distance, if you look towards the Malapert Massif, which is about 80 or 100 kilometers away toward the Earth, that the Earth itself will be visible from the settlement in the sky. If you look out what I think will be required, which are some windows. So it'll be here. There will be a need for an agricultural area for crop production and for recycling of the various key cycles. And of course, there's a number of elements that can be developed from lunar resources, and there are others which will have to be imported. And so low-cost transportation will be absolutely enabling for any kind of a lunar settlement. This is the approximate concept model that we are envisioning, which is based on, in this case, a cliff dwelling in the American Southwest, the Anasazi people, and the idea being that through a combination of tunneling and construction using technologies exactly like were discussed in contour crafting, that this is how we can quickly develop both a settlement, quickly, i.e. in 25 years, and a volume for agricultural operations. This just gives you a look at what it would look like if you were looking from Malapert Massif back in the general direction of the Oasis One. We've also got planning, which we'll be publishing, having to do with a spaceport to support the Oasis One and the fuel depot to support the spaceport. And then, of course, there are various locations in this vicinity which are permanently shadowed and have the prospect for ice mining. One of the best is this one, which is in this diamond shape, because the terrain in going from Oasis One to this permanently shadowed region where ice has been detected is relatively, I won't say quite, it's relatively benign. And so you have you have the prospect of surface access to the ice deposits and the ability to bring back the extracted ice for processing and turning it into propellants and atmospheric materials and so on. And with that, Madhu, I think I will stop. I think that's about 10 minutes. I'm sorry if I took a little too long. I'll just say that we are looking at also looking at the economics for such a settlement and how all of the prospects for operations and services and so on might knit together. Okay, thank you very much.
Thank you, John. You're so rational that I can keep my horses. We want this done tomorrow.
Yeah.
Thank you, John. We are off to our next speaker, and that is M.Morris. I want to tell you that a couple of years ago, it was not too long ago, that I started to see some incredible images coming out of this firm called Surge. And I think Michael will tell us more about all the good things happening before you share, Mac. Well, welcome to the Space Architects Gathering, Michael. You're.
You can hear me?
Yes, we can.
Greetings, everyone. I'm here with my colleagues, Christina Ciardullo and Rebecca Pailes-Friedman, but in the idea of just trying to be time effective, but it's just going to be me speaking to you today. So
hi, everybody.
And then because I'm in the west of Ireland, I'm going to be dropping off the call. So hopefully my colleagues can remain in the event to participate in the Q&A. But we also have a couple of other team members that we're working on this project that we're going to share with you today, the Lunar Lantern. Vittorio Netti and Mahsa are also here and can also potentially address some of the questions that may come up if
thank you all. Go for it.
Also not able to stay. So thank you so much. I'm just going to go ahead and share my screen. Okay. Share. Everybody see that? Is that visible?
Yes.
Great. So I'm just going to jump in and we're going to just start by showing you a video. Can everybody hear this?
We are the light that travels beyond to the moon.
The volume is low.
An extraordinary environment requiring extraordinary architecture. Search Plus introduces the Lunar Lantern.
Is a way to increase the volume?
Our contribution to ICON's
I'm looking at that. I
the
can't.
NASA-funded research and development program for a space-based construction system to support future exploration of the moon. The moon, harsh and hostile. Extreme temperature swings between 127 degrees Celsius to negative 238 degrees. Hours of seismic activity in the form of moonquakes and micrometeorite impact, all within a near atmospheric vacuum. For a permanent lunar presence to exist, robust structures will need to be built on the moon that provide better thermal, radiation, and micrometeorite protection than metal or inflatable habitats can provide. In order to achieve this, Search Plus designed responsive and resilient structures to be built using ICON's Olympus construction system and 3D printing technology.
Oops, sorry. Sorry, I'm going to go forward.
We are the light that travels beyond. To the
Oy.
moon. An extraordinary environment requiring extraordinary architecture. Search Plus introduces the Lunar Lantern. Our contribution to ICON's Project Olympus, the NASA-funded research and development program for a space-based construction system to support future exploration of the moon. The moon, harsh and hostile. Extreme temperature swings between 127 degrees Celsius to negative 238 degrees. Hours of seismic activity in the form of moonquakes and micrometeorite impact, all within a near atmospheric vacuum. For a permanent lunar presence to exist, robust structures will need to be built on the moon that provide better thermal, radiation, and micrometeorite protection than metal or inflatable habitats can provide. In order to achieve this, Search Plus designed responsive and resilient structures to be built using ICON's Olympus construction system and 3D printing technology. The Lunar Lantern Outpost consists of habitats, sheds, landing pads, blast walls, and roadways. Landing pads, thought to be one of the first lunar structures, will need to contain and control the supersonic and subsonic dust ejecta created during launch and landing. Search Plus's design offers multiple strategies for both dust mitigation and dust collection in printability, form, and function. In order to replicate the Earth's daily circadian rhythms and seasonal cycles, the Lunar Lantern utilizes a fiber optic system, which captures the nearly perpetual light at the moon's south pole and modulates it in both brightness and color temperature. The interior of the habitat is organized vertically with 3 designated levels for work and exercise, dining and social, sleeping and private spaces. The Lunar Lantern employs 3 key structural components. Base isolators at the foundation are employed to dampen seismic activity. Externally deployed post-tension cables apply compressive stress to the 3D printed regolith walls. And a protective double shell called a wiggle withstands ballistic impact and shades the sun. The Lunar Lantern concepts aim to exceed the factors of safety for its inhabitants in support of mankind's first extended mission on the moon's surface.
So sorry about that little glitch at the beginning. If you may know a little bit about this project, it's part of the Project Olympus, working with, commissioned by Icon Build out of Austin, and under the sort of guise of the Moon to Mars Planetary Autonomous Construction Technology, or MPACT team, that we are participating and developing concepts for habitats, infrastructural components, and landing pads, including landing pads for the lunar surface, for the lunar mission as part of that. And the project was largely site agnostic, as well as thing, and we were working with Icon's gantry system. I'm trying to move this forward. Is this moving forward? No, why is this not moving forward? There we go. The project started, I'm just going to go very briefly. This is almost a lecture by itself. Our colleague Christina Ciardullo sort of led this part of the project, which actually what became the catalyst for the MPACT project when we went to NASA after our successes with the Centennial Challenge competitions. We went to NASA to sort of start to build our, to begin to full-scale test some of our concepts. And we just started developing this Earth-space relationship and these sort of Venn diagrams. So I'm giving you a little bit of the background of the project, because I think the video, which was today, I think was the premiere of that video to you all, is the sort of thing. So we really looked at this sort of Venn diagrams in terms of construction technology, material innovation, sustainable operations, sustainable and scalability and human factors. And so this is a kind of a paper and a presentation perhaps on its own, where we were extensively looking at that. But as John was mentioning, and the previous speakers were mentioning, it sort of combines a lot of that information about the moon. And so speaking to the choir, I'm not going to go into too much depth here, but we did a lot of extensive background. In fact, it really takes us an hour to get through the general presentation of what we sort of tapped into and thinking about it. But we were basically looking at these four main factors: adaptability, flexibility, resilience, and multi-use. So I'm just going to be very brief with this. And so we were also working with the sort of timeline of, even though we were not, our project didn't specifically ask us to do this, we felt that we needed to do a lot of background material and precedent study, and also beginning to figure out with the technology readiness level, the TRL, how we could actually fold into the existing Artemis mission and project timeline to put boots on the ground. And we, although we were site agnostic, we did an extensive site analysis, sort of looking at precedent in terms of these, putting these lunar reconnaissance orbiter maps together with illuminance, topography, and temperature, beginning to look at that, as you saw in the video. And sort of we looked at a lot of different architectural precedents, particularly from the 60s on up, but in the RLSO2 precedents in particular, in terms of siting, and beginning to come up with master plan strategies, although that was not our charge in this project. So we're going to move on. We kind of covered the sort of landing pads in the video a little bit, so I'm not going to go into that too much today. But again, our charges were sort of, we took a larger view of this: planar surface construction, shielding, habitats, and utility shelters, in addition to sort of looking at the landing pads. And it was really an opportunity to begin to start talking to public and private sectors between NASA and obviously, you know, the Blue Origin, SpaceX, and Dynetics in terms of the sort of landing pad. I see that my lander at the bottom fell off the slide, but I'm sort of moving them around. They're all attached, but basically working with, you know, this information about the 17-degree, 3-degree dust plume mitigation in the sort of landing pad. And then quickly moving on, sort of like looking at all of the different construction technologies, from jacks to lift tilt-up prefab panels, to pressure vessels, inflatable and post-tensioning, foundation systems, and then looking at the different issues of the sort of capstone, the sort of overhang angle issues of building a pressurized habitat solely out of ISRU materials. So we, stuck on this. So I'm going to move forward. Sort of looking at then just developing a series of sheds. We sort of use the project to build our own vocabulary in terms of beginning to think about how we would actually develop the architecture along the sort of different class missions, along also through the timeline, and what would be ready to do in a few years' time versus ultimately, you know, several decades down the road. So it's not moving forward so easily. Oops. So we really, you know, part of Search's thing is that we're very interested in humanizing the spaces that we make. So we draw a lot of inspiration from biological sources. And in this particular case, you know, we were looking at pine cones, sort of seed cone relationships. And in the end, you know, because we had to introduce expansion joints into the Whipple shield, I found this direct correlation between our diagrid on the outside and this actually called Sputnik sea urchin, appropriately named. But began just looking at this sort of, you know, human factors aspect. And if we're going to send people into space for a long period of time, I think it's Search's, our firm's mandate that humans are positioned at the center. And so we sort of look to both space precedents as well as Earth precedents, and beginning to think that. We spent a long time doing a relationship between form optimization, relationship between the program and the printability issues, and the sort of relationship to that, to the habitat in particular. And this is sort of what we call the hero section of the habitat, which basically shows the elements, the Himawari fiber optic system, the Whipple shield, the post-tensioning cables, the 3D printed wall, the pressurized material liner, the window facing Earth, 3D printed foundation, parabolic base isolators, and a motorized spool for the tension cable. So you'll see this coming up again. This is sort of habitat requirements, structural analysis. So again, responding to radiation, seismic activity, extreme temperatures, and meteorite impact in relationship to what we were designing. And we sort of used these three basic things that you saw in the video: base isolation, post-tensioning, and a Whipple shield, to address some of these, the seismic activity, the sort of pressurization of the actual printed sintered regolith, and then the Whipple shield to deal with micrometeorites, but interestingly enough, also to deal with the sort of temperature. And a lot of our structural analysis, as was referred to earlier, that the sintered regolith could turn into a glass-like structure, we kept it at a sort of lower melting point and sort of produce a sort of ceramic. So a lot of our structural data are based on the fact that we would actually produce a ceramic sintered material. And this is something that is also simultaneously, as part of the impact team, is also being worked on. But this was our own internal analysis, both on the sort of seismic loading. The weight of this thing would actually have been probably okay, we found out, but there are certain issues of the sort of pressurization that you'll see in terms of the relationship of without post-tensioning on the left and with post-tensioning on the right. And you see you get a lot more blue by the added sort of cap. And this was also part of the deployment. But more interestingly enough was the sort of our preliminary studies of the 6-inch deflection that happens relative to the thermal loading on the actual printed regolith. So this is a really kind of an interesting find, and sort of really felt like it kind of really encapsulated this relationship between our Whipple shield shell, the sort of diagrid, and the relationship of the internalized habitat, sort of offering not only ballistic protection, but protection from thermal expansion and its sort of replaceability. And essentially what we found out, even from the Whipple shield, is that we had to introduce these expansion joints, which we're sort of currently continuing to work on to develop. So just in terms of its siting, again, it was sort of site agnostic, but we were sort of more or less leaning towards the sort of precedent of the lunar South Pole. and looking at sites, obviously, for those 3 criteria that I mentioned earlier. Flatness, but we were just looking at very basic integration between the fairing of the payload and the sort of rocket, and how we would get these internal core structures delivered from Earth. We were also looking at how our structure could, obviously we sort of developed the centerpiece, the level excavated, but we were looking at it in terms of different possibilities of terrain and then expansion in terms of first floor to second floor airlock systems that could offer connections to laboratories. So this habitat was solely developed as a habitat, but because we saw that laboratories should be separate structures if there is laboratory work being done. Just an animation of the construction sequence. So these sort of these leaves, if you were sort of would be replaceable should there be meteorite impact. And then one of the big internal debates that we had was whether the Whipple shield needed to be printed simultaneously or separately as per the diagram, like sort of from the inside out. So you have the left showing the simultaneous printing and the right showing the sort of sequential printing. So this was a big debate that we had internally about how the habitat would need to be protected while it was being built from this very thermal expansion that it was experiencing from the heat, the tremendous heat exchange.
How are we doing on time?
I'm done.
Michael? Oh, great, perfect. Oh, this is great. You know, pineapple is my favorite fruit. I have a large pine cone in front of our home too. But wonderful presentation.
Mine is always on my desk.
Okay, great. Thank you so much. I know every one of those authors you put on there. Melody Yashar talked to my class just not too long ago, and she was a presenter at the last event, I think, right, Ken? But anyway, thank you so much. Wonderful presentation.
Sorry about the sound in the video. We have to pump that up a little bit.
Base isolation is critical, Michael. I'm glad you addressed that. All we have to do now is worry about the dust, but that's another day. With that, we are going to Rodrigo in my favorite place of the world, Hawaii. How are things in paradise, Rodrigo? Microphone.
Things are great here, Madhu. Early in the morning right now. We're finally getting some sunny days after a lot of rain, but things are really good here.
Go for it.
Well, thank you, Madhu, and aloha to everybody. As Madhu said, I'm reaching to you from Hilo, Hawaii, the big island of Hawaii. I'm going to be talking to you about some of the work that we have been doing here at Pisces. We're a state agency located on the Big Island. Our main focus is to develop the aerospace industry in the state. We all know what ISRU is all about, you know, collection and processing of use of local resources and materials that replace materials that would otherwise be brought in from Earth. And as you all know, ISRU, it's not a really new concept. We've been doing ISRU for thousands of years. The thing is that when we go to the moon or Mars, we're not going to have as many resources as our predecessors have had in new locations here. But one thing we do have plenty of is regolith. And the nice thing about regolith is that it's readily available, easy to access, does not need to be processed. Just basically bend over and scoop it up and you have it in your hands. One thing that we have here in Hawaii is access to plenty of a good Mars or lunar simulant in the form of our basalt. Hawaii has been used for many years back from the Apollo days to do analog testing of hardware, equipment, instrumentation, robotics, mobility testing. And as you can see from this graph on the bottom of the slide, there are strong similarities between some of the basalt that we have here in Hawaii and some of the lunar and Mars soil samples that have been analyzed, which makes it a good place to do some testing when it comes to ISRU applications of regolith. One of the areas where we have been focusing our research is on sintering of Hawaiian basalt. And it's got many applications that have been already discussed in some of the previous talks, from launch pads, paver manufacturing for thermal waddies, re-entral thermal heat shields, radiation shields, flooring tiles, tools and parts, construction blocks, thermal insulation, paved surfaces. There's a lot of applications for regolith sintering. Our original work with sintering goes back to 2015-16, where we joined forces with Honeybee Robotics and the guys at Swamp Works at Kennedy Space Center, where we built a landing pad from start to finish. It was all built through teleoperations. It was made with interlocking tiles made from sintered basalt. So it was all meant to be a proof of concept to see if it's possible to build a launch pad, full-scale launch pad, with just in situ resources and be built telerobotically. So we had several findings from that project. One, it is possible. We were able to build the landing pad. We learned a lot from the design of the pavers, as well as the material that we utilized. The interlocking pavers, you know, the material proved to be tolerant to the velocities and the heat from the exhaust of the rocket motor. We submitted the tiles to a static rocket motor test. The design had some problems that caused airlift of the tiles once the hot gases penetrated underneath the tiles. It got through the joints of the tiles. But fortunately, the impact paver got pinned in place by the exhaust of the motor. And what we found out after we tested that impact paver was that the material did not suffer any significant degradation or loss of material due to the velocity or the heat from the exhaust of the motor. This also showed us the importance of you know, a couple of presentations have talked about using tiles, interlocking tiles for launch pads. Sealing the joints between the tiles or doing some kind of grouting to prevent the hot gases from infiltrating in between the tiles is going to be a critical part of the design process of a launch pad if it's going to be using sintering tiles. As far as properties of the basalt goes, the first generation of sintered basalt we built is that orange reddish sample on the top left, on the center left of the slide. And you can see from its properties, flexural strength and compressive strength, it lies somewhere in between residential concrete and commercial concrete. As we advance, we develop a stronger type of sintered basalt, the one on the center and right, that has significantly stronger structural properties than the first generation. We're talking now about 5,800 PSI of flexural strength and 30,000 pounds of compressive strength, which makes it stronger than specialty concrete. We've been working with that material and testing it for launch pad material. The picture on the bottom right is a tile we tested with Maston Space Systems in California. There's been a learning process in how to develop this material. The second picture from the bottom shows some of the initial work we had. And we had a lot of cracking and fracturing on the tiles. We later learned that the cooling process is just as important as the heating process. And we've gotten to the point where we can now repeatedly produce tiles of consistent properties. Now, this material also has the characteristic that it can be machined. So you can do some reductive manufacturing as well. Right now, we've been focusing on mold, creating our tiles in molds in a conventional kiln. As you can imagine, it is a very energy intensive process, which is a downside to sintering. One area that called our attention, there's a lot of talk about doing sintering both on the moon and Mars, but very little attention seems to be given to the mineralogy of the regolith that's going to be used. So we started looking at that, and the first thing we thought is, we know that not all basalt is created equal. it's going to vary. So we start collecting samples from various commercial quarries and analog sites here on the Big Island to see what the variations in mineral composition of basalt was. And we found that there is indeed some significant variations. What's interesting here, if you look at the Hawaii Puna A compared to Hawaii Puna B, these are samples collected from the same quarry. And if you look at the magnesium oxide variation, it's quite significant. We found out that that quarry is located in the joint zone of two volcanoes, Mauna Loa and Kilauea. So depending on how deep you mine the basalt from that quarry, you're going to be collecting basalt from one volcano or the other. And the basalt, depending on the volcano source, it's going to vary. So we found out that there are chemical or mineral variations in the composition of basalt. What does this have to do, or how does this affect the sinterability of the material? It turns out that it's quite significant. As you can see, the bottom three are three samples sintered from three different quarries, all three sintered at the exact same temperature. And we have one sample, Bolton, that was just completely junk. I mean, it would fall apart in your hands, which is pulverized. The other one, PTA, is a little bit stronger, and then Glover is a much stronger material. So the variation in mineralogy does have effect on sinterability, which then follow this reason. If we're going to be talking about sintering on the moon or Mars, we need to find out what the composition of the regolith is at desired locations to do that construction, and see if that regolith is suitable for the sintering process. Right now, we are working on using a mineral-based binder and aqueous solution. We just were notified that a proposal we submitted in collaboration with Mahsa Space Systems for an STTR has been selected to develop a low energy additive manufacturing process for launch pads. This new binder that we're utilizing has several benefits. One, it reduces the mold deterioration that we're having problems with right now. It significantly reduces the sintering temperature of the basalt. It can cure in lunar or Mars environment without the need to add additional heat. It's got the potential for additive manufacturing through extrusion. And the binder has the potential of being synthesized on Mars, not so much on the moon, or it'll be harder to synthesize on the moon, but definitely it can be synthesized from Martian regolith. It will require the use of water, so that's kind of the trade-off. You can do low energy additive manufacturing, which reduces the energy demand, but you will require to use water for the manufacturing process. That's what I have right now. I don't want to take too much time. I know we're running a little late. Here's my contact information. If anybody has any questions or would like to reach out to me, I'll be more than glad to communicate with you. I will try to stay towards the end, until the end of today's talk to answer any questions. But if any case, I have to leave, here is my contact information, and I'd be glad to share information with you.
Thank you, Rodrigo.
Yes.
Thank you, Rodrigo. You know, one of the things you want to do, look at this. I have the one that you machined for me. Maybe that's where the trick lies, in shaping structures just to fit. And thank you so much for your talk. We are off to our next speaker, who is joining us from New York. And that is, that's right. Thank you, Rodrigo. Daniel Inocente is extremely busy at the storied Skidmore, Owings and Merrill. Welcome, Daniel. Is there snow?
Thank you.
Is there snow outside?
No, it's very sunny, so I can't wait to get out.
I'm glad that's over with. Good to have you. Please continue.
Yeah, thank you. Thanks for having me.
You're welcome.
So I'm going to be presenting something that I came up with and pitched to Madhu called integrated tectonics. And I think it's important for all of us working on space architecture and the ideas behind space architecture to sometimes step back and think about the impact that these concepts can have on Earth and terrestrial applications. So I wanted to start with first thinking about how, how does architecture impact cities as a whole? Because urbanism, it's changing dramatically. There's tons of energy being used, tons of material. It takes a lot of ingenuity to build cities, to build structures, to build inhabited environments. And, we have great examples. We have examples where density really creates a lot of requirements from every discipline working on, different parts of infrastructure to bring together their expertise and to, make cities viable, and also to make settlements viable in extreme environments like in McMurdo Station. And so the kinds of logics, I think, and the kinds of ideas that we produce to build these interventions have to be very integrated. They have to be thoughtful, and they have to look far into the future. When I have the privilege of working on projects across scales in my role at SOM. And so I've had the privilege of working on large, tall towers, master plans, airports, research projects, space architecture projects. And I think the most valuable thing that we can bring to the table is, really the idea of design integration and finding ways to leverage the context that we're working in, whether it's environment or even technological context. And so these are just examples of, projects that I think have a lot of applicability to space architecture when you think about the design approach. And what I mean by that is, there's very complex structures. Space architecture is also very complex. And we have to think about environmental performance, energy, sustainability, materials, construction techniques. There's so many parameters that we have to piece together. And what I'm showing you here is an example of, how sometimes my mind works. I'm connecting different drivers, different forces together to try and generate architecture in a very thoughtful, but also in a very integrated way. And this is my, maybe it's a messy process, but it's my process. And as much information as I can gather and integrate at any given moment in my projects, I try to do that as efficiently as possible. And so, just thinking about examples of how we approach it, we do simulation for environmental performance. We look at planning, we look at the distribution of different spaces to create comfort in different environments. We look at constructability, looking at how pieces of buildings come together, looking at the environmental impact, looking at how potential energy can be transformed into something usable for an architecture. And we're thinking about these, and we're applying these logics to large scale structures. And there's a lot of ambition for these technologies in the future for space architecture. But if you think about them in terrestrial terms, there's also, I think a lot of challenges that we still have to deal with. Although there's, some great solutions in terms of energy production, we still have to figure out how do we make these technologies more efficient so that we can make them viable, for terrestrial applications. Structural efficiency, another big thing, the amount of structure that goes into any building, concrete, the mass required is just tremendous. And cities produce and consume so much concrete, which is a great CO2 emission material. We have to think carefully about how we use these materials. And at the same time, we're starting to push the envelope in terms of manufacturing. Here we have examples of using polymers to do 3D printing, using robotic printing, looking at how geometry and new additive manufacturing techniques can come together, can work together to make structures more efficient. And so what this does is it puts in context, I think, what's happening to architecture, which is it's being reimagined through new systems, new methods, new materials. And what does this mean for space architecture? What can it mean? So it's an opportunity to expand the scope and scale of architecture, but really to completely recontextualize the purpose and the meaning for what architecture can bring to future inhabited environments and the way that we build them. And the project that I'm gonna talk about here in terms of space architecture is one where we looked at our nearest neighbor, the moon, and we worked together with the European Space Agency and faculty at MIT to come up with a concept for what near-term space architecture could be. And what you see here is this very aspirational idea of taking a completely fully integrated habitat architecture, bringing it to the south pole of the moon, and making use of proximity to resources, proximity to energy, and looking for opportunities to conduct science, but at the same time, designing an architecture which brings a level of humanity to it so that you can work and live in different ways that sometimes is a missed opportunity in current forms of space architecture. And so, the context, a big driver. We have tons of potential energy if you know how to place your structure, if you know how to place your settlement, but we also have a lot of challenges because the geography is very complex. Getting equipment there is extremely difficult, but at the same time, we also know that there's some new vehicles, new assets being developed, like super heavy lift launchers that could potentially change the character of space architecture, bringing new, much larger pieces of architecture to our nearest neighbor, the moon. And the approach that we developed with ESA was, it's a very kind of methodical approach, but you have to start with assumptions. You have to think about, well, what kind of infrastructure do you need? You kind of have to anticipate that there's going to be a certain level of infrastructure already in place. And then you have to come up with a concept of operations. What does that mean? That means you have to define how different systems operate through different mission phases. And the habitat is only one of those components in that entire concept of operations. But this defines the requirements and the design approach to how you design a habitat. And so in our case, we looked at a potential habitat for four to six people for a mission duration of up to 300 consecutive days. That is a very, it's a very long duration. But during the process, we learned that we had to rethink how long you can actually support an occupied habitat for, because there's other hazards like radiation. And also you need to be able to supply, the crew with cargo, with food, with water. Some of those things, they take other subsequent missions. And so you have to think about how you tie everything together. A good reference for us was looking at the International Space Station. There's a lot of really great examples of how you build pressurized structures out there. And there's also other concepts which make use of inflatable technologies. But this is just the beginning. At the same time, we're also looking at how do you test, how do you launch, how do you dock, how do you land, how do you deploy this kind of architecture? And all of this, it came to us in the form of a hybrid type structure where we tried to leverage existing pressurized technologies for rigid metal structures, but then also found a way to integrate in an inflatable shell. And I won't go into too much detail on how these pieces come together, but there's some information about that. The mission components, like for any kind of architecture of this scale, you do need to consider what kind of launcher you're going to use. If it's something that weighs more than 40 metric tons, you're starting to get way beyond what we can actually deliver to the moon. But then if that's the case, if you're thinking about large payloads, then you have to conceptualize, what does a lander like this look? What does a lander for this kind of architecture look like? What kind of landing pads do you need? What kind of tugs do you need? You need also construction equipment like mobile cranes. You need power sources. You either need energy like power stations that can collect solar, in which case it becomes a large amount of surface area for solar power, or you can use fission reactors. So there's concepts out there about using fission reactors to produce energy. And we took all this into consideration, and we came to terms with the fact that infrastructure is a huge driver in how you think about space architecture. But at the same time, we wanted to approach this with a very human, a very experiential approach. And so we took a look at what kinds of programs do you need inside the space architecture. You need livable space. You need to be able to work. Most of the time spent inside of the habitat is going to be very much planned ahead. And so the kind of work and the efficiencies that you can get out of the way that you lay out spaces, that's something that has to be thoughtfully put together. Go ahead.
Assalamu alaikum, Steve. من باید برم USC دفترمو خالی کنم.
Just to continue, architectural considerations, we looked at a wide range of parameters for this kind of, for this project. And this is what you see here. It materialized in a configuration which really tries to make use of the internal volume, centralize the space, and also try to distribute different things like line of sight, communication, airflow, lighting control. All of these different features have to be integrated into the habitat and have to be, well within reach. You have to make use of the space efficiently, but you also want to make sure that people have enough, mobility and ability to interact with each other in different ways. In this case, what you see here is you see a concept for kind of like a pod. When you think about what does a bedroom look like for space architecture, some concepts they try to create these units where you have, like a typical bedroom unit like you would in a Manhattan loft or apartment. But in space, because every cubic meter of volume is so valuable, you really want to come up with a completely different idea. And we try to do that here. I'm going to skip through some of these, but I think structural analysis, going back to the idea of integration, is a very important one. Here we looked at using FEA analysis and finding the stress lines and articulating those stress lines between the rigid frame so that when you start to come up with the way that the straps would overlap, because we're thinking about using Vectran straps, for example, for the structural layer, the directionality and the way that they deploy is extremely important, and you have to follow the stress lines very, very efficiently. And the structural shell that we looked at, when you look at examples of inflatable shell structures, most of the time you're going to see just the structural and the pressure vessel layer exhibited. But on top of that, you also need the thermal, sorry about that. On top of that, you also need the thermal protection. You need MMOD for micrometeorite impacts, and all of that increases the thickness of the structural, the material that makes up the external shell. And so coming up with ways of packing all that material together is something that we looked at carefully, but I won't talk about it too much in detail here. Power was another one. So we looked at how much power would you need if you only depended on solar energy, for example. You would need a lot more surface area than you would if you only depended on a fission reactor. But at the same time, a fission reactor is also a smaller mass compared to the amount of PV panels that you would need and the mass associated with that. And so, there's trade-offs that you can think of. Yes, solar power is abundant if you're at the right altitude, but it's also less efficient in terms of how much material you have to get there to be able to create that power station. Of course, radiation is a big factor here. And so we looked at how do we reinforce the structure, because inherently, a metal frame and structural shell technology only has so much radiation protection, so you have to reinforce it. And we talk about using ISRU to reinforce our habitats. And so we did do some studies on how you build a structural shell around the habitat, and I'll show a little bit about that in the next slides. Life support is also very important. Looking at what kinds of life support systems you can include, where they can be integrated. Are they part of the the habitat permanent structure, or are they part of the rack systems that get deployed after? There's different ways of configuring life support systems, and at the same time, there's more advanced ways of thinking about life support, like food production, for example. And so if you really want to advance those kinds of technologies, you have to have the right experts involved, and that's what ESA provided. And so this is a demonstration of what the unit looks like. It's a fairly large structure. It's a 4-story structure. It inflates from 8 meters to up to about 14-meter diameter. And so that's a fairly large structure compared to other habitats out there. But the amount of pressurized volume is close to 600 cubic meters. And the habitable volume, after we've extracted all the volume consumed by the racks and equipment, is about 390 cubic meters. And so when you think about this kind of architecture, like what would be the first habitable space architecture, in our opinion, it needs to be a large structure that can host a wide range of activities. It needs to be able to enable future construction. And those kinds of activities are long-term. You know, it takes time to build. And so with the right habitat architecture, you can really start to explore and make use of resources and build these kinds of structures that we're talking about, whether they're underground or above ground, and make use of other technologies that can be more generative to help us define what these structures would look like, you know, given the constraints like mass, thickness, construction technique. All these things have a huge role to play. And what you see here is just an approach that we use to define, you know, multiple objectives and look for ways to articulate those geometries. This is an illustration of how we envision construction happening over time, but it does take a lot of infrastructure. And so with the right infrastructure, with the right transportation systems, we can start to get these pieces of equipment and capabilities there so we can build these tall structures. But at the same time, you know, habitat systems will need to be developed and they have to be integrated. We have to find a way to think of new architectural technologies that can make these habitats viable in the future. So that's it for my talk.
Thank you so much, Daniel. So much to chew on in your,
yeah.
in your beautiful, beautiful rendition. I just made some notes. Those solar panels need to go someplace else because in about a day, none of them will produce power because of all the shadows that come on there. Even if you shine, even if you place them, oh, maybe there are ways to do this, but it's wonderful. You brought up some very important building issues because you work at SOM. Thank you so much. And I know that you experience these problems.
Yeah,
we
absolutely.
have to run because we are a little bit late, but our next presenter is Giuseppe from Sydney. Hello, Giuseppe.
Yes, I'm not sure if it's good afternoon here. It's 6:30 in the morning in Sydney, Australia.
And you're looking just good and ready to go. So we are moving from orbital habitats to lunar habitats, and now we are slipping into interplanetary. We are going to start looking at Martian habitats. Go for it.
Thank you, Professor Madhu. Thank you for the invite. It's an honor to be here, and it's a very exciting topic. Most of the presenters I know, was lovely discovering new people, and also been citing some of the professors, your own work and my own work, because I'm now part of a Moon consortium, and reading all of your papers, just know that I'm one of them, and it's really interesting all the work that you produce. So thank you so much. Yes, so my name is Giuseppe Calabrese. I'm originally from Italy, and I'm currently in Sydney, Australia. And what I wanted to present today was a competition that I entered for the Mars City Design Award, where I resulted basically the first winner of the architecture section. So basically, this competition was organized by Mars City Design, which is a sort of a red carpet innovation platform for any ideas to do with the red planet. And the brief was sort of how to support human life on Mars for a period of 2 years for 9 astronauts, and through sustainable produce farming. So everybody approached it in a different way. And what I came up with was a structure, but I think the design is never linear between A to Z. It always goes in various shapes and forms before coming together. What we had to use was a software called CMOC, and CMOC is it's a sort of let's call it a scalable interactive model of an off-world community, and it has decades of NASA data. So it's all englobated in this software, and in this software we had to choose how much dry produce there was, how many batteries, what the crew quarters were, the greenhouse, various sizes, various parameters. And at the end, it would tell us, you know, you had 9 green men, or there were going to be 9 red men at the end of the software when it was running. So lots and lots of data had to be imported inside of this software to basically see if the mission was successful. I have a background in earth construction. I did a thesis in heritage and restoration in Italy and study of earth buildings, also published in that sector. And so my approach was, rather than creating a beautiful structure, was mostly to do with ISRU, so seeing what were the capabilities of the site. So went through, again, a lot of scientific papers, also imagery, so satellite imagery. So until a Perseverance will send us some physical samples of what is there, I went through the papers of the professors that were presented and published. And what was interesting to see was this area in purple that came up, which was called smectite. Now, smectite, when I saw that, I got really excited because it is a fantastic material to build with. It's a particular clay. And with the experience in earth construction, what I did is basically use this clay to form up some bricks. Bricks, of course, mortarless bricks that could just be clicked together in some sort of Lego system. So the easiest approach would be they could just be clicked together. Also, information regarding the, as a professor said earlier, about contour crafting and basically the printing different shapes that would be able to sustain themselves without collapsing. So my specialty in architecture was in heritage and restoration, and particularly the study of old structures. And so the Nubian vaults in this case would have been a perfect structure to a self-sustaining structure that doesn't need a structure to hold it up. So lots of studies have been done and are being taken forward on the angles and the materials. So my suggestion was to follow that of most of the papers, which was an angle of 40 degrees. And so, of course, this is all using the smectite for the building building blocks, and for the printing of the roof with the basalt and the silicone, all materials that are present on site. I then came across a physician named Michael Smith. He has 35 years experience in AI. And basically what he does is applying natural intelligence to the development of regenerative agricultural systems and renewable energy. And he's already done this on planet Earth. He's created what's called the green powerhouse system. Now, this green powerhouse system is actually, it's quite a success story. And he basically came up with this big system where waste gets transformed into a series of byproducts which can be soil amendments, energy, electricity, and then we have biochar. And biochar is a particular material where the microbes of the soil can live in. So the idea was for this competition not only to create a structure that was successful on planet Earth, but also to create a structure that would be successful, on Mars, but also to be successful on planet Earth, because what the National Geographic has been studying is that we're in a situation where we have a soil depletion. The soil depletion will be happening in around 60 years. Because of the population growth, basically we are trying to get from our soil as much produce as possible. So we are using more herbicides, more pesticides, then we get superbugs, and then we need more fertilizers. So it's a vicious circle of soil depletion. Unfortunately, this cannot continue. And also then we have extreme temperature changes also on planet Earth. So this structure, what it does is basically creates a shelter for the greenhouses. The greenhouses will be inserted inside these buildings made out of regolith blocks. All of this will employ robots and humans. So real-time telerobotic systems is proposed as economical, viable strategy for this Martian system. So co-robots and robotic systems are designed and operated at real time using telerobotics. And so this will be done all from our planet. And basically we would send in the payload the ISS cylinders, and then they'll open up inside the structures. Then maybe at the end I'll just share a few seconds of video so you could see how all this operates. But you can see on the bottom left image, basically these ISS cylinders will slide inside these structures, and then they will inflate, and they will have already seeds inside. And so the seeds will sprout, and when the astronauts arrive, they will already have an amount of produce. Now, with the CMOX software, we couldn't simply put in whatever we wanted. There were certain type and varieties of plants that we had to select. I went for certain types of plants that were not consuming too much water. For example, if I selected wheat, the wheat takes months to come to maturation, and also it utilizes a lot of water. So at the end, my 9 astronauts will become red. So I went, the selection was critical. I went for mostly a Mediterranean menu, as I'm Italian. So this was basically the layout, as you can see, for the 9 people. And there's also habitation. And in a radial shape, we've got the solar collectors, as you can see. Expansion went up to 22 people in the bottom image. I also included insects because, of course, you need the pollination for the plants. And we need seeds, so we need a bank seeds. All of this will create super seeds, because our seeds, we think we're trying to create something for Mars, but I think we need to think Mars is creating something for us, because we will have a super seed, a seed that will be able to resist in certain type of gravity, radiation, illumination. So it will be a very resistant seed. And once we get those seeds and we plant them back on planet Earth, we will have a really boosted crop and really resistant. So I see it the other way around. I'll just go through the next one. So what we've got here on the left-hand side of the image is sort of this hive where I can see sort of some snowflakes which are sort of fractal shapes that can be repeated. And of course, the system had to be able to expand. So radial roads that don't interfere with each other, and each with its own green powerhouse, so that if one system fails, all the rest keeps on moving forward. On the right-hand corner, top image, you can see basically the, you can see the, let's go back to the previous screen. Yeah, you can see the Jezero crater and basically the delta with the area of the smectite. So the location of the buildings, the storage containers, and then radially I put all the solar farms. So we needed a huge amount of solar panels to create the energy as a backup, because not only there's a nuclear energy generator, but also the calculations for the solar farm had to be done. So there's a lot of science, a lot of papers that had to be read. It was not just basically pretty drawings. So you can see basically the layout of the whole system that protects from the radiation and the extreme cold ionizing cylinders. Okay, so here we've got a zoom in of the system. So pressurized areas, non-pressurized areas. Basically, the center of the green powerhouse is got these race courses, and these race courses are not not pressurized, and then they link together with an area that is pressurized that contains all these greenhouse cylinders. The race courses are 6, and they will be approximately half a meter in depth. Here we have more details. Of course, the Nubian vaults of the green powerhouse also, they'll get 3D printed. We've got a vast area for the photosynthetic core. That is the first thing that will be mounted. A whole system that will has already been demonstrated to be able to work. And so it's just been all included and molded with basically the whole system. There's plenty of space and heights, so for maintenance and expansion of the units. Also did a lot of study in terms of heights and communication between all the pods and transitional ways. And you can see the ISS cylinder has also a transparent cover. This is very important because not only we are trying to get light from the sky, we are also trying to use the solar collectors to suffice for that lack of light. So as you can see from the bottom left image, the light will penetrate through the sintered the glass, and then it will go through the ISS cylinder. So we're trying to use as much light as we can in different sources of light. And of course, the LEDs, they don't need all the spectrum. So there've been studies done on different types of spectrum and the quantity of light that they need. So inside, you can see, of course, the ISS cylinder that's been selected based on the payload and the current missions, what sizes we have and how all of this can expand. Of course, here then we've got sections, elevations, and some images of the Mars blocks, and pics of what I thought could be basically the rover. And the rover has these different attachments. So one would be a machine that selects the smectite, then it compresses it in compressed Mars blocks, it microwaves it, and then it lifts it. So we have another attachment with a scissor hoist that stacks all the bricks, and then it has another attachment with a mechanical arm, and it 3D prints this Nubian vault, and basically all done with telerobotics. Here we have other sections of the building, and you can see these ISS cylinders and how they link together with the produce, and the scissor hoist on the top right, and getting the construction underway. The bottom image is basically what I envision with all the dust storms that sometimes can last up to a year, and so this structure eventually, these Nubian vaults will be covered, and also part of the walls, which will just protect further from the radiation and micrometeorites. So these are some views from the internals, and you can see the algal race pool on the bottom left-hand side, sectional, axonometric on the top left, and the bottom is basically the summary of the competition that this application would have to be for, not only for Mars, but also for Earth. So if it's permitted, I'll just do the video, basically very few seconds. I'll just go through very few elements. Let's see if I can pull this up. Full screen. I won't show it all, of course, because we don't have time. I'm just going to go through basically the construction of the bricks by these the rovers, and so the basalt flooring, as you can see, gets 3D printed, and the photosynthetic core, and with all the bricks basically stacking up. So you can see that being formed. All right, so then I'll just fast forward to basically all the sections here that we'll have. So how all this floor plan is organized, with the very core of each section being independent from each other.
If you're showing us the video, we're not saying anything.
Right, sorry for that. Let's okay.
And
all right, sorry, I'll just, can you see that?
Archives. Go for
sorry,
it.
Can you see that? Perfect.
Yes.
All right, so I'll just go back to here. We'll just go a few seconds. So I'm not going to go with the audio. We'll just so basically here we've got the machinery. The rover is creating the 3D basalt pod, and then the machinery keeps on 3D printing it. Photosynthetic core at the center, getting ready, and then all the bricks in the formation being created. Okay, so I'll just fast forward. So here we've got basically the center and all the various parts and how they are formed and what their role is. And the machinery, then lifting up all the blocks and creating all the structure that will protect the ISS cylinders from the extreme weather temperatures. And then here we have the attachment creating the 3D basalt roof and the solar penetration, solar collectors. And I think with this, I'll probably conclude, and I'll leave it to the next speaker because I don't want to take too much time. But thanks so much for having me, and I look forward to also the future presenters.
Thank you, Giuseppe. Your presentation is fine, and we are running late, but you know what? I could see this for a long time too, because it's so beautiful. And all of us, I think Daniel said it clearly up front, the environmental impacts and environmental stressors, they're really stressors, will condition many of our designs. And so we need to pay more attention to what the environmental conditions are, both on the moon, Mars, and my favorite place is Titan. So all of those places. Thank you so much. And I want all of you to know, Giuseppe is a violinist. So you better ask him about that later. Thank you so much. We are off to Paris now to listen to Jim Rohn. Jim, are you with us?
Yes. Hello, Madhu.
Oh my goodness, we are very sorry. We are running a little late, Jim, but please.
Yes, very fine. No worries. Thank you for inviting us. I know John, that is part of the team, is also one of your students. So it's a great pleasure to be here. Good morning, everyone. Good day, and maybe good evening from wherever you are today. So my name is Jim Rhoné. I'm a lead designer at Interstellar Lab, and so I'm going to present what we are doing currently. Let me share my screen.
Go for it. How is the weather in Paris? Are you still wearing masks?
It's, unfortunately still wearing masks, and not going better those days. So yeah.
Oh, it's going to get better, Jim. Just wait. It's going to get better.
Yeah. All right. Can you guys see my screen? Yes. All right. So to get into what we're doing at Interstellar Lab, so we are designing and building pods for sustainable living on Earth and in space. So a bit more precisely, we are developing space-grade environmentally controlled modules to grow food while recycling air, water, and waste. So when we get to the strategy about the whole constructed system, we are designing the modules so that they can actually be operated as autonomous and standalone pods. So that's what you see here on the picture. Every of these single units can actually work by itself. They also can be plugged together in order to form a complete eBIOS. So what we call an eBIOS is it stands for Experimental Bioregenerative Station. So it's a combination of different units that together form a closed loop environment that are able to sustain the life for up to 10 people. These different units, as I said, are autonomous. They are plugged with airlocks to the central piece in order to prevent any contamination between the different units. So to get into the functionality of each of them, we first have an aeroponic unit, which is where we're gonna dedicate it's gonna be dedicated to the food production mainly. So that's where we're gonna have all the A-frames and towers that are going to grow fruits, vegetables, and leafy greens. You then have the greenhouse unit, also partly linked to the food production, since that's the place where we're gonna be growing trees, mostly for fruit production. But it's also very much related to the psychological needs of the crew when actually running the mission to get a glimpse of what Earth actually looks like. When we then switch to the treatment unit, that's where the human waste and the inedible part from the food production are going to be collected. So that's where the black water is turned into potable water with a lot of filtration, probably reverse osmosis as well. And also where we actually turn human waste into nutrient solutions. You then have the habitat units. That's where most of the daily life of the crew is going to happen. Bedrooms, sanitaries, kitchen, the training and sports as well. This place is probably going to be 3D printed, slightly different to the rest of the pod. You then have the circulation units. So there are two main ones. The tunnel, which is able to connect to another station. Again, the main goal of this design is to be modular, but also very easily deployable and scalable. So the idea is to be able to plug different units like this and be able to, in the end, grow a kind of a city. And you then have on the left the small entrance, which is a dedicated unit to access the station or to exit it when you want to go into in situ exploration. Last but not least, yeah, the connector. So the mission control unit. It's the masterpiece of the whole station. It's the connector. So inside that part, you're gonna have a whole area dedicated to mission control. A lot of screens actually gathering data coming from all the different units to have a kind of a global overview of what's happening in the station, even though all the pods are autonomous. So you have every single entrance of this connector are like standardized plug that you can, and so you can actually arrange every unit as needed. So now let me deep dive a bit more into what we are really doing right now, which is the development of our first unit that we call the biopod. It's an advanced greenhouse and food production module, so it's the one you saw in the previous slides. There are going to be two different biopods, two different sizes. A bigger one, which is the one we're going to use for eBios, and a smaller one that we are actually now using for testing, prototyping, and also developing on Earth for Earth applications. So the first goal of what we're doing right now is actually being able to recreate a very sealed environment. So the envelope of the biopod is composed of two main parts. We first have a composite base, ultralight and resistance. That's where all the systems are going to be sitting. And on top of that, you have a soft membrane that is air supported. So with a slightly overpressure inside. The interest of this membrane is made of high performance materials, so with very good insulation properties. It's made of two different materials, one that enables to have a total opaqueness, and the other one to get as much light as possible, so with a very high transmittance. So once we actually managed to get this seal environment, the idea was to develop the system that's gonna run inside, so everything related to the Eclipse. The reason why we decided to have this composite base is really to be able to sit all the hardware and systems in it. So in the end, when you want to run this closed loop environment, you are actually trying to balance the light, recycling the air and the water. So that's where we're going to have the closed loop water treatment systems to make sure that every single drop of water that we actually bring in the biopod is used for the crop growth only. So we have systems that are able to filtrate, so UV filtration mostly, and then the humidifiers, of course, to capture the water in the air and get it back into the system. We have our autonomous nutrient dosing system that is also in the composite base, and on top of these hardware part, have a raised floor access where you're going to be sitting the aeroponic system. I'm going to get back on that a bit later. But that's where we're gonna have the LED lighting system that are actually playing with the sunlight that we get and trying to balance the light inside the domes so that we get the optimized light for the crop growth itself. And last but not least, we have the advanced atmospheric system that is making sure that we get the proper balance between O2, CO2, and nitrogen, and we're actually playing with CO2 boost as well to get a maximum yield from the crop. So getting back to the crops, once we managed to actually create this seal membrane plus having this Eclipse system running, the next step is actually trying to develop the technology that are going to that will allow us to grow the crops. So we are basically using high pressure aeroponic systems for vegetable and leafy greens, and a substrate based greenhouse that will allow us to grow small trees for fruit production. And all this as a controlled environment agriculture. That leads me to the fact that inside the biopods, we're gonna have a lot of sensors and controllers, and that combination will allow us to get to precision agriculture and predictive monitoring, knowing that we have a very data-driven approach. So our biologists are actually testing a lot of crops right now in a smaller version of these biodomes, just to get the proper data on the yield, on the specific condition that we need to grow this plants into. And that data acquisition will be combined with AI decision making and then embedded control system to make sure that we are actually able to grow the specific plants inside the dome with the right kind of condition they need. So in the end, all these properties from the biopods will allow us to save a lot of water, making sure that, as I was saying, like the single drop we input in the system will be used for the crop growth to boost yield, of course, since compared to traditional agriculture, we'll be able to grow crops every day of the year. And in the end, to reduce energy, since the seal membrane we are actually developing will allow us to really prevent as much as possible exchanges between external environment and the inside. So apart from the hardware we are developing, we are of course combining that with a software approach. So AI decision making was part of it, and we are also developing the interface that's gonna allow us to run the biopod. So the first part of the software is going to be a dashboard where we get all the data coming from the sensors and the controllers, just to make sure, it's kind of mission control as well, just to make sure that everything is running properly. That's also, and then the second part is the crop selector. So our software engineers are working on a specific algorithm that are actually scheduling, planning, and optimizing the crop management, just to make sure that we satisfy the nutritional needs for a specific amount of people on the crew over a certain period of time. So what you see on the screen is more inside of that, and the crop selector should be released pretty soon. So in the end, just to get back to the original mission and vision that we have at Industrial Lab. So we believe that what we are trying to develop will contribute to create sustainable living system. Either it is to start growing the next generation of farmers on Earth, or in a couple of years being part of the Artemis program and contribute to build the sustainable moon base, or a few decades from now being able to contribute to make the human a multiplanetary species, but still thinking about the Earth. So that's it. That's it for me. Thank you very much.
Thank you so much, Jim. It's a pleasure to see finally that we have come down to planet Earth. And this is a good reminder for all of us that one of the duties of the space architect is also to reflect on our population, on our species on Earth, about what it is that we are doing out there, looking out into space and creating all these magical things, which are impressive. But it's very important to bring that down to Earth and make it happen. The only thing I would say, Jim, is that I have a hunch that if you're going to do this underground, you're going to save a lot of energy. Okay, good. Thank you so much. Thank you so much.
Thank you very much, Madhu. Thank you.
And we are.
We can't hear you, Madhu.
You didn't hear anything I said?
And not after, Jim's.
All right, good. Good, go for it.
Oh, let me
Here.
Mm.
Can you see my screen?
Yes.
Hello, everyone. I'm Mahsa Esfandabadi, and I'm really happy to be here today with you. So, a little bit about myself is that I have undergrad of architecture and then master's of architecture. I have another master's of historical studies of Middle Eastern architecture, and finally I ended up in master's of aerospace architecture at SIGSA. And I'm currently doing 3 volunteer jobs. One of them is I'm director and secretary National Space Society of North Houston. I'm Capcom for MDRS, and I'm judge for Deep Space Food Challenge, which I really encourage you to participate. It is really, really interesting. And today I'm going to present what I've done at SIGSA with Dr. Banova and Professor Kennedy, and Professor Choops, and what I've done with Dr. Valentina Simini at MIT Media Lab.
Some of them are listening in, Mahsa.
Yeah, I know. I saw Valentina and Professor Kennedy's here
Okay,
too. So when we were talking about greenhouse, what exactly do we mean? I thought that we have 6 questions that if we can find a solution or answer to these 6 questions, we can somehow say that we're reaching to the point that we can really say we have finally come up with a solution of greenhouse design. So one of them is, what are we really going to grow? The answer to this would impact crew's daily menu. And then how we're going to grow them. And the answer to that would be how that, after we grow everything, how we're going to turn it into food actually. And what is the post-harvesting process? And then at the end, where exactly we're going to grow these plants. And the answer for that would be a greenhouse or an environment which needs to have human factors so that crew can enjoy that environment too. So I turn these questions into 3 categories: assumptions, systems, and architecture. So I was very curious about the plans that space agencies have provided. As you can see in this table, there are different plant lists that different space agencies have provided. I have the full plant list at the end of the slides. I can show you, but if you want the main source, you can check the paper below. That NASA has said that they have 3 different kinds of plant lists. They have the minimal, which you can see here, which has 13 plants, and then they have a moderate plant list, which is about 20 plants, and then we have the generous one, which is 36. So I was curious that what exactly is the difference between these. So I went through all the plants and I found out that there's a huge cultural difference and diversity here. That, for example, if you can see, the US, even in the smallest, in the minimal plant list, they have 4 different types of grain in their food diet for the astronaut. But for example, Russia has just 1. And this, for example, it increases to 6 when they're providing more variety of plants, but still ESA and Canada, they're providing 2. So I thought that maybe just 1 ultimate plant list is not the answer to everything, that we can say, hey, if we grow these 10 plants, they can have enough food. And then I was curious that, okay, for example, if we want to grow potato and tomato and some, for example, onion, and the same time wheat and rice, they're not going to fit in the same pot. So I thought that since if we have the approach of including diversity, we need to have that diversity in our design too. So the first thing that needs diversity is the plant pot. The left, you can see one of the proposals that we did for one of the papers. But after the size of the plant pots, how many pots do we really need? There's a study from NASA, it's a report which says that If we want to provide 60% of the food from the plants for the diet, which is 2,700 kilocalorie, they need 46.5 square meter of cultivation area for one person, which means that if we want to have 4 crew over there, that would be 500 square meter of cultivation area, which, for example, if we want to have the same plant pots, it means that we need 1,784 plant pots to provide this much of food to the crew. So it's not something very small. It's not something that you can have it in a teeny tiny inflatable or even in a hard shell. So what can we do? One of the things that I was searching is that there is a total pressure in living zone area that we need to provide for the habitat zone. But is this really happening the same thing for the plants? It seems that no, plants really don't care what pressure is going on around them. As long as the partial pressure of CO2 and other gases are the way that they want, they really don't care. So if we lower the pressure of the environment that plants are living to, for example, 56.5, which is the pressure of the rover, or even 61, which is the pressure of the ISIS when they want to go for EPA, that would reduce the pressure in half, which means that we can reduce the launching mass less than a half, and then it means that we can have a larger inflatable structure that we can have more plants. So how would that affect the whole greenhouse and crew idea? I was checking how long crew spend every day for their surface missions in NASA's mission scenarios. So there are 2 mission scenarios, which says that in the one that you can see in top, there are 3 EVA scenarios that when crew wants to go to the EVA, they start from 101 kilopascal, and then there's a 20 minutes of 56.5, and then the pressure reduces significantly, and then they go to EVA, they come back to the, for example, the airlock, then they go back and forth. There's another scenario that they just lower the pressure, they go for 8 hours of EVA and 4 hours of EVA, and then they come back. So I thought that when we're discussing about lowering the pressure of the environment, as you can see in the lower diagram, if we lower the pressure of the greenhouse to 56.5, this 7 hour and 20 minutes or 4 hour, 40 minutes that they're wasting their time in their airlock by just staring at the walls and doing nothing, they can spend that time in the greenhouse. In the greenhouse, which already has that mass reduction and is very bigger and so on. So why we're not using this? Then after this proposal, me and Dr. Barnwell, we were thinking that, okay, if we're including the crew inside of the greenhouse, what will happen? So this is the whole greenhouse and food module. The rest of these all systems that you can see, these are the systems that we usually include in the greenhouse module. What we're missing is that food processing system. Okay, we harvested wheat, we harvested rice. What's going to happen next? How is that going to turn into a food? So we need a food processing system to go through primary process, secondary process, and so on, and turn that into a dish so that they can use it later on. How that would impact the whole design process? This is these 2 red ones are the impacts of having the post-harvesting process, and this black water is the impact of having the crew inside of the greenhouse module for that EVA time. If they want to use the restroom, or if they want to, I mean, they're producing some black waste. This is the diagram that shows how things distribute between the pour and the inflatable. When we're just providing water and power and air through the airlock, what will happen after that? So as you can see, lots of the main systems, they should be inside of the core because they need to have some pre-integrations, and the installation of those are probably very hard. But most of the stuff that are very volumetrically volume consumable, and they need to stay in inflatable, like plant pots, that they're very, very large, and we cannot really put them inside of the core. So we have inflatable and we have a core. What are the design options? As you can see on top, well, we have found in the previous studies that most of the design are based on 4 different types: mushroom, torus, and 2-petal versions. And as you can see from the this table, that each of these design, it has some pros and cons. So the petal version is very, very good when they are operating, carbonating, or in case of emergency. So most of the design that we see on the, I don't know, on the market or on the studies, they're just talking about the operation mode when the greenhouse is working 100%. So what will happen if something happens, if we have some fatal error in the system? If that happens in torus, for example, if meteoroid enters or penetrates the inflatable, we're done. The pressure is lost and we lose all the crops immediately. The same thing somehow happens to the mushroom too. But for the petals, if something attacks the inflatable in petals, we don't lose the other ones. We still have one. But on the other hand, for example, mushroom one is very, very good in deployment, and it's very, very mobile. So we were thinking, have we found the answer to greenhouse design? It seems that no, because if you look at the mission scenarios that NASA provides, there are different kinds. So far they have proposed 3 missions, which is exploration mission, science mission, and the, for example, actual living mission. So if we are thinking about having the exploration mission, mushroom would be very good because we can simply put it on a rover and we can take that greenhouse everywhere we want, and we can test and see if those plants are growing well over there or not. And when we don't have actual, for example, ISRU printed field over the surface, maybe the petals are really good because they are really good at emergency and they are lower in risk. But the torus, they have the highest the ratio of usable area comparing to the other ones. So if we really reach the level that we can have a settlement and we can have the 3D printed shelter, torus would be the best answer. The next, so we found, okay, what is the approximate design that we really want? Me and Dr. Sumini, we were thinking that, okay, how is that shelter going to happen? And we were thinking about how we can use the historical structures and historical monuments and use those aspects on with new approaches. So we found out that most of the domes that we see in the proposals, they're usually as called in here surface domes. These are the Persian domes divided in, categorized in different, based on their structures. So we were thinking that there are lots of similarity. We have a paper and presentation on that in about 2 weeks. And that there are lots of bathhouses in the desert areas of Iran and in the old Middle Eastern, that they are using the rib domes. And the structure of the greenhouses and their oscillation and their similarities to the greenhouse that we can have on Mars is very, very high. So we were thinking why we cannot, if we cannot use the rib ones. Are there any preference from the surface domes to the rib ones? So we thought that in the 3D printing process, and as Vittorio was saying, yeah, 3D printers are very dumb. So if we can do, if we can make a dome in a very, very basic way that people are doing it in the Middle East for thousands of, not thousands of years, but the oldest adobe structure in Iran is about 4,000 years. So if we can really find out how they build it and how it survived, would that be a solution for us too? So this is the ribbed one, as you can see. So the only problem with the ribbed one is having that mold underneath, and then you put the bricks on top, and then so the ribs are, I mean, the barriers of the whole pressure and the structure, and then you fill between the ribs with whatever material that you can find. So we start our study with 5 of the arches that we have in Persian studies. These are the 30 samples of the arches that we usually, you can find them in Persian regions. We picked these 5, and then we started designing patterns and nodes in Grasshopper to see if we can come up to the idea that how, for example, how many numbers of these ribs would be the answer, or what kind of pattern, the pattern that they're connecting together, that it affects as you can see, the middle circle in the middle, that the opening of the dome. Which of these would be better idea for our project? This is another, in the elevation of the rib dome, how that the different kind of patterns affect the opening of the top. And then these are the simulations of the dome that we calculated. As I mentioned before, we were thinking about lowering the pressure, so you can see different colors. If you notice the numbers underneath, we try to simulate with Mars regolith and with different inner pressure with different domes. In the deformation that you see is that because we turned on the oh my God, I forgot the word. I really forgot the word. To see what is exactly we turned on the deformation to see how these ribs will change and how we can control them if we really want to make it more practical for the Mars. These are different types. They're very, very interesting in visuals, and as you can see, the deformation is really interesting. They're all using the same span, but because we're using different types of arches, the height of them are different. So the span of all of them are the same. So what's the result in here? That you can see the arches and different heights and the span that is similar for these. You can see in this table, in this chart, that they connect together in some points. And it was really, really interesting that what will happen in these points. It seems that when we are having a lower pressure, this is the hemisphere one. Hemisphere is working really, really good. And comparing the deformation to the other arches and other domes, this performance is really, really better. But when we're hiring the pressure,
a minute to go.
It's almost the end. But when we hire the pressure, the arch number 26 is very, very close to the hemisphere. And in here, even arch number 11 is very, very similar to the hemisphere. So we're kind of proposed that if they're working the same, if the deformation is the same, why we're not using the different kinds of domes. So this is how we can see greenhouse systems and the structure in a new way. That's it. Thank you.
Great. Thank you so much, Mahsa. And now I want to tell you one little story about how all these people from Persia came to northern India and built a magnificent structure called the Taj Mahal. It's staying there. It's got an incredible dome with some of these beautiful features Mahsa mentioned. And guess what? They built it on the banks of a river. And so settlement is a very big issue, except that the Taj is still staying without any settlement. So now think about it while the next presenter comes on, and he's none other than my good friend, Phil Sadler. Are you here, Phil? Oh, I see you. Okay, good. Phil, I'm sure you'll have a lot of things to say about what Mahsa said, but we got to keep our time. I'm sorry we are running late. We'll try to catch up. Go for it, Phil.
Okay, how am I doing?
Come on screen and we'll tell you.
Okay.
I can see you.
Yeah. How about my slideshow?
Not yet.
It's coming up.
Coming up, okay. How are you doing, Phil?
Oh, real good, real good.
Okay. Oh, there we go. We got it.
Okay, I apologize, but I have to have those guys, Madhu, run my slideshow because I fell offline yesterday with a Zoom call, and I'm worried about it today. So anyway, I work at the...
Are you able to go to the university, or are you in your home office?
No, I'm at home.
Okay, go for it.
I work with the University of Arizona Controlled Environment Ag Center, and we've been working in greenhouses and in extreme environments for about 20 years. And these are our partners, and we've had a number of NASA contracts, and we had an NSF contract to build the South Pole greenhouse. Okay, next.
Phil, that part of the slide on the bottom, is it Apollo 11 or Apollo 17?
I'm not really sure.
Okay, go for it.
Okay, next slide. This goes back to 2004. We built and delivered the South Pole greenhouse. I worked out there earlier, and in '88 I started the greenhouse program. But this shows how isolated South Pole is. It's a good analog for space. There's nothing close to this facility for hundreds of miles. And everything has to be brought in by aircraft or tractor train, and very isolated. Okay, next slide. I built an original greenhouse out there in 92 or 91. And when they built the new station, they wanted a new greenhouse. So I work with Dr. Gene Giacomelli and the Controlled Environment Ag Center, and we developed this greenhouse, and it's still functioning today. They still enjoy it, and they're isolated for 7 to 8 months out there, and it produces fresh produce for them, because after about a month or so, they run out, and then it's just canned stuff and frozen stuff. So they really enjoy the greenhouse. Okay, next slide. Our students ran the greenhouse from Tucson, and this is Lane Patterson. He was my right-hand man through the whole thing, and he went out and got it going. But our students managed it from Tucson, and Lane was the first guy to grow cantaloupes at the South Pole. And on your right below is Jen, and that's Senator McCain. He was out there visiting, and he didn't realize that the U of A had built this this greenhouse there for him. But it was supported from Tucson, and it'd be very similar to what you might expect on the moon, where you have experts remotely directing the operation of the chamber. And the chamber itself is a robot. You can't do the physical stuff remotely, but all the set points, all the data collection, distribution of this data and stuff is all done remotely. And okay, next slide. This is what it looks like on the inside. It's inside the station. This bottom center picture is the hallway, and the people come and go, and it's got an environmental room where people can smell the, when you're at South Pole, everything smells like diesel fuel and it's extremely dry. And it's an environmental room to allow people to be there. And then it's separated from the growing area, which has CO2 enrichment. They bring bottled CO2 there to enrich it because the plants will scrub out most of the CO2 rapidly. And so how it works is it's got water cooled. Well, now they've gotten rid of them, but they originally, I developed a water jacketed high pressure sodium light for the bioplex at Johnson Space Center. And then we used it for this contract. And how it works is those trays, the lower trays pull out, they're on tracks that allow it to pull out when you don't have anybody in there. So it's basically two parabolas that is most efficient for using the light. Because diesel fuel at South Pole Station, which is what runs the generators, is about $20 a gallon when it's delivered there. So it's very expensive to generate power, and that's nothing compared to what it'll be like on the moon or Mars. So, okay, next slide. This is the NASA renderings of the most recent ones of greenhouses that NASA has generated. But the one on the upper right, that's a good likeness of Ray Wheeler. You know, he's our friend at Kennedy Space Center, and probably the most knowledgeable person that NASA has in space horticulture. But what you should take away from this is the amount of production that you see there isn't close to what the kind of density you're going to need for space. You can't justify having a chamber with that few plants in it. Okay, next slide. We were approached early on to build a greenhouse for the moon, and you have to know what the habitat's going to look like. You can't just design something and, you know, it's got to be integrated. It's so integrated with the rest of the habitat that you have to have something to work for. So we used the habitat demonstration unit. It's part of the HERA project now at JSC, but that was our starting point. And we developed these inflatable modules that radiate from the central hub for our greenhouse. You've got air exchanges, you've got water exchanges, you've got people that have to go in there and work. So it's real important to have some idea what the whole habitat looks like when you start. Okay, next one. And I've been making these modules, and the one on the upper left is covered with regolith for radiation shielding and micrometeorite bombardment. And the dishes up on top are solar concentrators, which collect the natural light and bring it into the station, the habitat, with fiber optic cables. And what's interesting is that with natural light like that and a hemawari type approach or a dish approach, you can split the spectra where you can take the PAR light, the photosynthetic active radiation light, and use it for your plant lighting and your interior lighting. But the other half of the spectra, you can turn that into electricity and into heat. So it's real important to, and if you have dishes like that, you can track the sun. If you're at the South Pole, you know, in one of those peaks of eternal light, it can rotate 360 degrees and track your sun. The lower pictures, that's sort of the membrane. It's going to be like a spacesuit with multiple layers of whatever for the membrane, and it's going to be pretty thick, I imagine. But there's probably going to be a format like on ISS. there is a specific format for all the ISS express racks to plug into. And I think that on the moon, you'll probably have the same situation where you have to be able to get to that pressure hole quickly in case you have a puncture, so you can get in there and patch it. Having a bunch of rigid materials that you can't remove is a real hazard. You have the express rack, you have to be able to grab it and pull it out of there within minutes, so you can get back behind it and put a patch on your penetration. Okay, next slide. We had a NASA grant called the Ralph Steckler Space Grant, and it was a great grant. And during that time, we built units and collected data, and this is a design. You can see in the upper left that it collapses to about a meter in length, and then it expands to 5.5 meters when inflated. So that was one of our original designs, but I've abandoned. This is obsolete in my estimation because too much mass. I've gone to a much lighter format, like you saw earlier with the 5 struts or spars. That's all you really need, because on the moon, the regolith is equal to about 600 or 700 pounds per cubic yard. I don't know what that is in metric, but that's about the same as the weight of the snow at South Pole. And on Earth, that regolith would be 2,900 pounds per cubic yard, but on the moon, it's only about 600 or 700 pounds per cubic yard. So it's very similar to snow, and you don't need a lot of structure to hold that up. The air pressure, if you have it somewhere between 9 psi, the air pressure is enough to hold it up.
Phil, we got 3 minutes.
Okay, next slide. Next slide, please. This is some of the crops we grow. We grow root crops. We grow potatoes, tomatoes. Sweet potato is taking over the chamber here with the red blue LEDs and the full spectrum lighting. Next slide, please. This is our best shot, and it was overtaken by the sweet potatoes, but this doesn't represent. This is about half of the type of productivity you need in order to justify having a greenhouse. Next slide. This is our data, and we've got a couple papers out on it. But what was interesting was that one day we got a maximum water condensed out of the unit of 47 liters of water. Ray Wheeler and Dan Barta years ago came up with the thing: if you can grow 50% of the calories for the crew, you can produce 100% of the water recycling and 100% of the air revitalization. Next slide, please. Again, our work is available on, the access through the web. Next slide. This is out of Biosphere. I've got an exhibit there where we have one of our 12-foot units there as part of the exhibit, and people come and we have like 100,000 people a year before the virus come and visit the Biosphere, and it's been real successful. It's been there about 5 years. Next slide. We had it out for 7 months at the Chicago Museum of Science and Technology, and then we brought it back here and put it in the Biosphere. But this is basically what it is. It's real lightweight, and the inflatable cover on the right is something to represent what the thickness of what a covering might look like when it's actually made. But we give tours, we have tours, and the students explain what's going on. Next slide. This is an express rack. I'm interested in membrane structures for inside the habitat. And this was a membrane express rack that I built. And again, this is obsolete. I got a new generation that I'm working on, but I am dedicated to, there's no reason to have a real rigid structure to put a bunch of plants in. So that's the direction I'm moving towards. It folds up the size of a large suitcase. Next slide. And this is my next generation module that I'm building, and should have it in 6 months. I should have it completed. Next slide. Okay, this is our crew and some of our people we collaborate with, and that's about it.
Thank you, Phil. Please say hello to Jean and Lane. I learned a lot from all of you in the past few years about how plants dictate a lot of things they need in terms of nutrients. I still recall Lane telling me that plants call for certain nutrients, and then they just take it. And these are living things that have lived billions of years before we got to the scene. So I respect plants. Anyhow, we'll talk more. We are going to our next speaker, who is none other than Mirha, who is going to join us from Milano.
No, from Bari.
From Bari, yes,
Yeah.
Bari. You're a good friend of Vittorio.
Yes.
That's right. Vittorio was your teaching assistant. That's good. Go for it, Mirha. So nice to see you.
Nice to see you all. 1 second. Okay, so before I start, I would like to say thank you to Mr. Madhu and all the AIAA community that gave us this opportunity to show our project master thesis. This thesis was born from the collaboration between the Polytechnic of Bari and SIXA department of University of Houston. The name of the thesis is Hive Mars, Design of a Hybrid Class Scalable Settlement on the Martian Surface, which has been done by Archimars group under the supervision of Professor Architect Giuseppe Calabrese and Space Architect Vittorio Netti. Before everything, 1 second. Okay, before showing the outpost proposal, it has been defined a mission architecture diagram that represents launch, travel, and landing phases. The diagram shows 3 phases of mission. The first mission, a robotic mission of Perseverance rover 2020. And for the second phase, the cargo mission has been chosen SpaceX Big Falcon rocket. And for the third phase, crewed part of the mission, NASA SLS Block 1B. It's a bit slow. The site chosen for our thesis project is Hellas Planitia, which is the biggest basin on Mars, located in the southern hemisphere of the planet. The choice of this site depended on a number of factors, such as depth, which allows to have a more moderate percentage of radiation than other areas on this surface, the reduced presence of rocks and the ground, and the presence of moderate reliefs, which makes the area more suitable for the development of a settlement and for landing operations. The most decisive factor in this choice of the site was the presence of water attested by the honeycomb terrain, a geological feature whose process is linked to the principle of ice ascent. The project is located in the central part of Hellas Planitia because it is the flattest area, and above all because the side surrounding reliefs, although moderate, provide a natural shelter from Martian weather such as sandstorms. The project takes the name Hive-Mars with the aim of resuming the physical characteristic of the honeycomb terrain of the chosen site and defining its principle of expansion. The concept is oriented northwest, and it shows a simplification of the project by identifying the areas necessary for the development of the latter, namely landing area, which is positioned 3.5 kilometers from the habitat. Then we have ESREU area, in situ resources area, which is positioned 100 meters from the habitat, and energy production area, which is positioned also 100 meters from the habitat. The last area is the habitat. On the top of the habitat and infrastructure design, we focused also on the construction sequence outlining appropriate surface elements to support the construction. This role is performed by the B family rovers, which include all the autonomous and semi-autonomous mobile assets. The design of each machine is inspired by epigenetic-based insects belonging to Apidae family, a peculiar genetic characteristic that allows insects with the same DNA to evolve in different physical features, designed to fit their role in hive societies. Each of the bee rover assets plays a different role in the construction process that we will see in the next slides. It was important to define all the stages of construction of the settlement, from the landing to the arrival of men. The Starship spacecraft payload lands in the landing area, releasing B family rovers for the preparation and exploration of the site before the arrival of men. First of all, Spider Explorer probes the entire area to ensure that the requirements are met. Later, the bee flattener rover flattens the road network, then in situ resources utilization area, energy production area, and construction area. In this way, the bee excavator and bee transporter rover reach the ISREU area where water extraction, oxygen production, and regolith collection activities takes place. The extracted regolith is processed inside bee processor and transferred to the bee 3D printer that proceeds with the construction of the protective wall of the landing area, roads, and the habitat. The bee lifter rover instead provides for the positioning of the architectural elements to be inserted during the phases of habitat construction. At the same time, the bee transporter rover brings kilopower and solar panels on the energy production area. Once the site is ready to host the first crew, SLS Block 1B lands on Martian soil. Upon his arrival, Archimedes, a pressurized rover, leads the astronauts into the habitat, which consists of 3 housing units, 1 main and 2 secondary ones, and hangar to protect the vehicle from the atmospheric agents. The future expansion is inspired by the territorial conformation of hexagonal honeycomb, infinitely repeatable, and able to tessellate the space and connect among themselves all the housing units. After analyzing all the types associated with the planetary habitat, we chose a hybrid one, the use of class 2 3D printed one for the external structure, and integrated with the class 3 inflatable one for the internal module. It was the most convenient in terms of cost and time savings and comfort. The external structure refers to historical models of the Nubian dome and takes the shape of a dome with an ogival section truncated at the top. Martian raw material, regolith, is used in the construction of the external structure of housing modules. The latter is collected by the excavator and transported inside the regolith processor. The material is mixed with a binder, glucose-based elastomeric polymer, which is extracted from organic and biological waste and solvents. The material obtained, Martian cement, is transferred to a 3D printer that proceeds with the printing by layers. The choice for a superior truncated dome was dictated by three main reasons. The first reason lies in the construction technology that was used, which does not allow the upper part of the dome to close properly. The second reason is of a structural nature, that this type of dome does not need support during printing. And finally, the literature on planetary architecture suggests inserting the right housing module only when the construction of protection against radiation, micrometeorites, and sandstorm has been completed. Therefore, it turns that the upper truncated ogival shape is the only one suitable for meeting these requirements. The construction of the dome structure begins with the excavation of a 1.6 meter circular hole that will host the habitat foundation. The typology chosen is the continuous foundation with a circular bed lower than the ground level, in which the internal shell will sit. Subsequently, the V3D printer will proceed to print the base of the external shell, starting from the foundation level. The first interruption of the printing takes place in correspondence with the ground level hatches placed inside the side connections. The V-lifter rover transports and places the airlocks undeployed. The rigid section of the hatches and airlocks work as support for the upper layers. A second interruption occurs at the windows level, directly transported from Earth and placed and positioned using the V-lifter rover. The printing of ogival dome continues after the placement of the first three openings, interrupting in correspondence with the upper ones, positioned in correspondence with the second and third floors. The upper part of the dome is truncated because the printing technique would not allow adequate structural support to close the shape. Furthermore, once the construction of the envelope has been completed, this shape allows the placement of undeployed internal module from the upper cavity by means of the V-lifter rover. In the end, a truncated pyramidal skylight is placed to seal the external shell. This element is inspired by the ISS dome and provides greater illumination of the internal environment. In particular, the shell presents a smooth surface on the inside, while the outside is modeled onto a parametric three-dimensional texture that allows a better thermal management and protection against micrometeorites impact. The choice of an external texture responds to two determining factors, such as the self-shading of the structure itself and the ability to retain the dust that is deposited on it. Over time, this dust stiffens the structure and also increases the wall thickness, resulting in additional protection. Once the class 2 protective structure has been defined, it is possible to establish class 3 housing module, which is part of the infrastructures brought from the Earth. A long-term stay requires a habitat capable of reducing the mass and cost of launching, and at the same time capable of guaranteeing large pressurized spaces to allow all human activities to be carried out. The choice for the habitat inside the regolith structure therefore fell on an inflatable habitat. Its advantages are remarkable. It is lighter than a rigid aluminum structure. It also allows greater flexibility of the internal layout and greater internal volumes. Also allows automated outfittings and easier assembly, manages better the thermal and structural stresses while keeping the weight low. So once the undeployed inner module is lowered from above into the dome, the inflation begins. Integrated air pumps the pressurization needed to reach final shape of the inflatable module. At the same time, through an automated mechanical system, the internal steel structure is deployed, starting from the deployment of the central core, then the floors, and in the end of the pillars. Okay. So a habitable module is obtained that occupies almost the entire internal volume of the external regolith. In the section, we can see the configuration of the inflatable module, which is divided into 3 levels of decreasing walkable area, accessible and connected vertically by a harmonious spiral staircase placed in the center inside the core. Each of the levels has 3 windows arranged on axes of 120 degrees, which do not so much perform the function of illuminating from the outside, but rather that to offer a man a view to the outside, partly freeing him from the sense of closure and isolation. The function of illuminating the internal environment is instead performed by a circular skylight mounted at the top. Thanks to a system of automated shutters, the skylight opens during certain hours of the day to illuminate the second floor and partially reach the lower floors between the gaps of external shell and inflatable module. Each level fulfills a specific function. The ground floor identifies a common area where the main control activities takes place and where the scientific research area and the medical area are located. Observing the drawings, we note how the internal arrangement of these rooms derives from the presence of 3 airlocks connecting with the other living modules arranged on 120 degrees axis. The first floor is the most private area, containing the living area and the sleeping area, while the top floor is a semi-private area where leisure, reading, and sports activities takes place. Archimar's team has also put forward a design proposal for 2 green systems, one aimed at the production of food and the other characterized by a virtual garden. Both proposals are part of a more future hypothesis belonging to a future phase of expansion that sees human settlement change and grow into a colony. The first green system is housed inside the ogival dome in Martian regolith, already used as casing of the housing inflatable module. In this case, also, a structure is obtained that is raised on 3 levels. Connected by a central core. Each level identifies a central green ring, which houses a core wall, a hydroponic cultivation system given by columns of vases. On all of the vases, there is a protection shield that contains the purple light, grown light, specially applied to the bottom of each vase. And one outer green ring that houses a number of different racks. The second green system has a more psychological character, and everything is aimed at ensuring the social and mental health of future inhabitants of the red planet. bridging the distance with the Earth and reducing the feeling associated with inevitable isolation conditions was the primary purpose of the Archimars team during the design phase of the second green system. The interior has one large common space in which holograms project three-dimensional images of typical terrestrial gardens. To conclude, it is possible to learn from our ancestors, and at the same time, with the help of knowledge and advanced technologies at our disposal, it is possible to inhabit an extreme place like Mars. By limiting the extreme characteristic of the environmental that characterize Mars, such as distance from Earth, the need to build in the most standardized way possible, the need to limit space and use resources, men will be able to build the first human settlement, which will in the future characterize a protected archaeological site. Thank you for your attention. Thank you very much.
Thank you, Mirha. Somebody asked me the other day, hey, what's the difference between a systems engineer and a space architect? The answer is very simple. Space architects draw like crazy.
Yes.
And that brings me, thank you so much, Mirha. We hope to continue this discussion. At this time, I want to introduce Professor Michael Fox from Cal Poly Pomona. I was invited sometimes to review the good work that he and his group of students have done in the past. Welcome, Michael. The floor is yours.
Hi, Madhu. Can you see that okay?
Yes.
Okay. Anyway, thanks. Thanks for having me. I have to say I'm a terrestrial architect. Even build a lot of buildings on Earth, and I just want to say that you know, for me, this is super interesting because of I suppose looking and understanding at designs with limited resources and environments that are extreme leads us to a much higher respect of nature here, and respect of human beings, and generating eventually improved life on Earth. And so really I'm interested in bringing home these lessons learned, and it's great that we do these a lot, you know, interdisciplinary projects. I think the one I'm going to show right now, I think, is our sixth one that we've done, and they're all vastly different, and you know, sometimes I'm kind of drinking from a fire hose. I think the good thing is that we are in LA and we have great people from JPL like Madhu and Scott Howe and Mark Cohen and Brent Sherwood before he left town. And all these guys are just great because they come and kind of share like their wisdom from years of doing this space architecture with the students and help us kind of keep on track. So this was one earlier one. This is a lot of fun that we did, which was a deep space habitation model. And, you know, we like to build things, physical models and real big kind of lo-fi analog projects. That kind of led to another one, which was designed for a handhold foothold, which was a different type of grant where we got to go and test it in 0G, which was a lot of fun, and take the students along with me. So this one I'm going to talk about was with this XHAB program, which is for student exploration of kind of specific things related not always do space architecture, but often, and when they do, we always try and do them. This proposal specifically addresses the challenge to create a habitation system that has commonality in both the in-space and then the surface habitat design. So the crew are familiar with the layout, the function, location of everything in the surface habitat when they then arrive on Mars. We kind of start off with a lot of different concept designs, again, kind of drinking from a fire hose to kind of get things right. And this is when, like, all of our really consultants are extremely valuable. Mark Cohen was like very involved in this project, came to our class a lot, really kind of helping us keep on track. And
Mark is in New York with his granddaughter. So he says, sorry, he cannot be there.
Yeah, I miss him. And so these kind of, these sort of preliminary designs were then kind of initially compared, you know, and evaluated on the relative merits of against a pretty inclusive set of criteria. And this then gave us a framework for evaluating like different design potentials and different engineering options. And then we kind of down selected, and we went through this down selection process like 3 times, and until we kind of had a particular design. This one we sort of went with was we called it the CR1, and the most important aspects that need resolution here were the transformation mechanism that would allow the IPV to function in 0G and the Mars gravitational environment, and the structural integrity. The program layout had to be designed allowing all the components to kind of be pre-installed with full functionality before and then also after transformation, and allowing a limited mobility on the Mars surface once it's there. And of course, the transformation mechanism was kind of central to this. The idea is that there's 4 of these sort of truncated cylinders, and then they essentially unroll and can connect together and make larger habitation. So, you know, there's scenarios where this becomes much kind of larger as an environment. And here you kind of see a diagram of the unrolling, and looking at kind of a lot of different variations in terms of just the geometry for how this could unroll. Looking at program configuration, kind of interesting, with, you know, the adjacencies, you know, before unrolling and after unrolling, and of course this being kind of the Martian gravitational analog on the left. And so we then kind of developed the drawings to a fairly high level of resolution. And we used, I think this is one of the most interesting parts is, you know, we used a lot of exploratory means to kind of understand the design and develop the design. So it's not kind of show and tell of making the drawings, but it's really kind of, you know, understanding things and evolving the design. So we kind of very early on made a pretty sophisticated BIM model, and we had like great consultants from Geary Technologies, which is now Trimble. We made a full-scale prototype with AR to understand the ergonomics and the human scale, and then a fully detailed kind of VR model to understand, again, the ergonomics and human scale of things, and then small scale robotics, understanding different mechanics, and a physical prototype at 1 to 10. This is just some images inside the VR model, which was great, you know, because it was used as a design tool for kind of, you know, understanding, you know, how you can walk around it. And it's super interesting to kind of move around in VR in the rolled position and then have the unrolled position and kind of walk around in a low G version of that. And then the AR version, I think, also was pretty interesting, where we were using basically a lo-fi kind of but full scale kind of version. And then you get the AR version that when you put on the glasses, you have all the furniture and everything within the context of the physical environment. So this was actually pretty interesting to explore. I've done quite a few things with AR since. And then looking at small scale robotics and kind of looking at how the unrolling mechanisms would work, and then also the mobility. This one was, it was in an exhibit at the San Francisco MoMA. There was a space exhibit. There were some other really cool space architecture projects there. I went up and saw it. And then, looking at some of these drawings in particular, that they were transformative drawings, and meaning looking at not just static conditions, so how it could unroll, and then kind of the full 3D like model. This was actually the VR model, and then making a 1 to 10 physical prototype, which was actually really valuable in a lot of respects, in understanding the transformation of it. So this is, again, 1 to 10, so pretty small. But then we took it out to the desert and kind of did a little demonstration of it. Anyway, that's this project. These are all the students who learned a lot. This is Mark Schulitz, who worked on it a lot.
Wait a minute, I see me in there.
Yeah, there you are. I think it was, and there's Ed McCullough.
Miss Ed, don't we? We miss Ed.
Yeah, we do. Anyway, so thanks a lot. I think that wraps it up.
Thank you, Michael. A fantastic presentation, and I like your screen, the way you are appearing with. I think is that a technique that you're using? You're coming through with your background fuzzy.
Blur background. Yeah.
Blur background.
Blur background. Yeah.
I love it. Okay, great. Thank you so much, Michael. We got to run to our next presenter, and that is somebody very special. Zooming in late in the night from London. I'm happy to introduce to you Xavier, whom I've known many times over his incredible visuals. We are so happy you're awake to present. Xavier, hope you had some tea. Hope you had some PG tips or something.
A glass of wine, actually.
Oh gosh, okay, good. So good to see you. Go for it.
Hey, thank you, Madhu. Thank you so much for inviting me. You guys all hear me well? Yeah?
Very well.
Oh, good. So, well, thanks so much for inviting me. Today, quick introduction, my name is Xavier, and I am an architect. I'd like to call myself an architect, not really a space architect, like what Michael said, because I think architecture itself, I think, really is enough to, as a profession, to be in space, right? And that's what I want to talk about today is the value of design, the value of architecture itself, when we move into space in this field. And on top of that, I'm also going to talk about the importance of sustainability and recycling and reusing materials in space. And I'm going to do that with one project. And the project I'm going to talk about is Hassel Studios' proposal for the NASA Centennial 3D Printed Habitat Challenge. So our project exists out of two elements. It has a 3D printed shell structure and then an inflatable, unfoldable, pressurized, prefabricated element underneath. Now for this one, we were actually a little bit naughty because we went against the brief that NASA put forward because they wanted us to look at a 3D printed pressurizable system. We weren't quite comfortable with that because knowing from our Earth examples and normal architecture, like this amazing Felix Candela's shell structure, that has been made in situ, the 3D printed shell structure, not with robots, with lots of people, to a certain degree of accuracy, right? It can't be super accurate. You don't have the performance that you would do with building this on Earth. And then underneath, you would get prefabricated elements like facade systems made on Earth to much higher precision. So we think is that combination is really the clue in building habitats on Mars. So this is our proposal. As you see, we didn't bring a massive 3D printer. We're bringing much smaller a swarm robotic set of printers, all working together to 3D print our shell structure years before our astronauts arrive. And there's 4 different ones that we have. I'm not going to go into detail of them, but we were a little bit surprised the moment we saw this rendering, because this rendering done by our visualizer showed our robots that just done their job. They finished the shell structure. On the foreground, the right-hand side, they're all there. We created the first boneyard of robots that are not necessary anymore. And that was a shock to the system, really. And it really started us to think much, much harder in how we should behave on Mars, how we should reuse and recycle things. Back to the drawing boards. We redesigned our robots. We made our robots now still autonomous, but now modular. We could actually make different types of robots with a certain amount of standard set of elements. It's a bit like a Lego system for robotics, right? Having a few legs, having 2 diggers coming together, a sinter station coming together, and we create ourselves a 3D printer again. Now, we have different elements. We have a scouter, which is kind of a one-wheel scouter. We have then our digger, which is completely based on the diggers developed by NASA in the SwampWorks team. And the last robot, I'll show that one, is our printing robot then that will use microwave technology to bring it all together. Let me just do that quickly here. There we go. So our habitat, we thought, as lots of people talked about, the idea of a view to Mars is actually important. So how are we going to do that? We know how important this piece is on the ISS, the cupola, and how this is actually protected with this kind of mechanical system that protect the windows. We thought we could have a non-mechanical way of solving this problem and more of an architectural one. So we looked at this, a beautiful courtyard in the Mediterranean. What's so great about this? Well, you can get sunlight in, you can get indirect light in, but not direct light, because of course on Mars, that would actually mean much high radiation in your habitat. And on top of that, you create a beautiful view across your habitat. Here doing some tests using the tools we use in architecture on Earth, checking radiation from, this is a tool that we normally use for sun radiation, see if a building doesn't get too hot. We did the same thing, but actually looking at the actual gamma radiation. And here's our habitat. Now we bring in indirect sunlight and we are able to get still that view across the habitat. So a habitat exists out of that shell structure. Then underneath, we get these 6 inflatable pods with some connectors in there. And if we go look a little bit in detail, we'll see that we organize them as a big donut, but then each pod is also organized in a circular way, in a radial way. And that's for a particular reason, because we looked at the ISS and we thought the way how we have the racks, the science racks, and how they all fitted out in all these kind of cylindrical modules, we think that's actually suboptimal. I thought we could do better. And the way to do that was by looking at not a very high-tech solution, but looking at archives of libraries where you have these racks that are able to open up and close up. And that's a way to kind of really use space much more optimum, right? So we maybe get away with this idea of having all these corridors in the ISS in space habitats. And that's what we did. We have a radial system, a rack system that exists out of these movable radial racks that could be either a science rack, but could also be storage, or it could be a greenhouse. And we can see that here in each of our renderings. This is our science rack, astronaut doing some work on maybe setting up an experiment, but once he's done, he could probably even move that out of the way and go into another one. And we did it the same way for our greenhouse, movable radial rack system. And the same thing, we kind of use that standardized system for also our gym, and this is also the private sleeping quarters of the astronauts. So always the same system, so it becomes really interchangeable. And we even have it here in our workshop, a very important place, because people are going to have to fix stuff. You know, you can't get a spare part. So we have on the background, we have a large Delta printer, we have some laser cutter there, and also we have a sewing machine, as you can see. You might wonder, why would we have sewing machines? Why would we do that for? Well, I believe we should actually do that as well, because we have to think about reusing and recycling materials. There's already fabric there. This is a picture, of course, taken from Perseverance rover, landed with the parachutes. Why not just think about reusing those materials as well? So for this project, we collaborated with Kriss J. He's a fashion designer in Hackney in London, and that's what he's been doing for the last 10 years. He actually designs clothes and makes clothes made out of already used materials. He sometimes uses blankets, use military equipment, and also parachutes. So we used his pieces from his archive that we could then use in our photo shoot for the renderings, right? That was in our studio in London. And Chris got so interested in our project that he even then based his new collection, his spring-summer collection 2020, on our design. And this is some of the pieces that they made for that, which was a really cool collaboration, really. Then further, furniture, right? We thought, well, why not we actually make our furniture over there on Mars and reuse waste plastics from food packaging or from science experiments? Again, we collaborate again for this. We collaborated with Manuel Jimenez Garcia. Here, me and him working at Norman Foster Foundation just over a year ago. And we decided that he would design special furniture made out of recycled plastics. And that's actually his factory and his design studio just outside Madrid. So we worked with him to create this chair, this kind of chaise longue for Mars, made out of, this is actually made out of recycled medical equipment here. And then he designed all the furniture for Mars habitat, as you see here, all 3D printed. The first collaboration is really important. So for this whole project, we also collaborate with Cranfield University, with Professor David Cullen and his students. His students do the students in system engineering. And that was quite important because we could ask them interesting questions. Beginning of our project, we looked at creating an inflatable as a support structure for the construction process of the 3D printing. We thought it was actually a bit of a dumb idea. We went away with it. We got rid of it. And we started looking at other more known architectural examples. This is Sana's Toshima Museum. That was constructed by using earth formwork. So what we then did, we said, okay, well, let's do it that way. Well, let's do earth formwork and fill the whole shell structure with loose regolith, and the loose regolith becomes a support structure. But we thought, well, this might take too much energy, this might be too long. So we then worked with the system engineers to kind of understand how long this would all take. And they came back, put all their spreadsheets in, and because they work with spreadsheets, we work with drawings, and they came out, I'll take a year longer, which was fine. So I'm actually saying that, and Madhu, I like your comment earlier on about this difference between architects and system engineers. Well, we did work with system engineers. The right-hand drawing is, of course, done by us. And well, the left-hand drawing was also done by us, but with input from all the spreadsheets of the system engineer. So this really drawing, this kind of dual drawing shows the architecture and the mission architecture and the system engineer together. So we really kind of thought this duality is actually really important. And then we're really lucky in the end that we were invited by the Design Museum for the famous Moving to Mars exhibition that is now, if you go to Stockholm, you can see it there, to actually build a full-on one-to-one. And what Michael said, yeah, we're architects, we love to make mock-ups, we love to build the real thing. And we thought that was important to do for us. Again, the racks were actually movables. People could come into the exhibition, move the racks, try on the clothes even, pretend they're astronauts, and even that view out, as important, that was so important. So we had this massive video wall you see on the left-hand side that was all built in real time in Unreal gaming engine, and you can see other astronauts, digital astronauts, be walking around in the other habitats. And really, and the light even changed from day to night, and so forth. So really to get that real kind of immersive experience. Thank you. I kept that within the 15 minutes, didn't I? Even shorter. Madhu, you're on mute.
Thank you, Xavier. I was just going to can you slide back to that last image where you showed the microscope?
Oh, this one?
There, that one. Do you see a beautiful 19th century microscope sitting there? Microscopes don't look like that anymore, but you know, it tells you, you know, when a child sees this drawing, she or he would want to live there because those are the kind of things that we grew up with, and it's a delightful presentation.
It's good. Well, we did actually check, Madhu, what we would take. The microscope might be a bit, but we actually worked with Sanjeev Gupta, who is one of the scientists on the Curiosity rover mission.
All right.
And we asked him, you're going to tell us what should be in that lab. It was actually really nice. He even gave us one of his hammers that he used as a teenager. And he said, like, you know what, that hammer, I would still take that to Mars. So some of the bits that are in there, and he kind of had all his kind of scientists working with us to saying, so what would we really take? The microscope, maybe not, but all the other bits, they said like, well, they probably would take stuff like that.
Yes, and talking about microscopes, I am also a fan of microscopes, Xavier, because I think a geologist would be it would be very helpful. And now most of our spacecraft are starting to get more and more magnification into their visual systems. Thank you so much.
Thank you.
We'll be in touch, Xavier. Let us go on to Denmark now. Sebastian is with us, and I see him right there. Go for it, Sebastian. You know, we want you to tell us what time it is over there,
it's
whether you're sleepy or not, and then go on with your incredible project. Folks,
hi, thanks so much.
You're welcome.
Thanks so much. Do you hear me? Do you hear me okay?
Well, it's a little spotty, but we can see you. I'm going to get offline if that'll help a little bit. But I want to mention, now we are moving from Moon to Mars and now to simulators. And Sebastian's group has done some fantastic work. I'm so happy you're with us. Go for it.
Thank you so much. Our internet today is a little bit spotty, so I hope that you can hear me. I'm just gonna present. Here we go. All right. So I come from Saga Space Architects, and today I'm mostly going to talk about our lunar analog mission to northern Greenland that I just got back from in December. My name is Sebastian. I'm one of the co-founders of Saga. We have grown from originally only two architects to a larger team that you can see here. I really hope you can see the screen. The internet is a little bit tricky on me right now.
If you go off,
this is
Sebastian, if you turn off your camera now that we have seen you, will it help our case a little bit better? I'm wondering. Go for it.
I'm gonna try. Did that help a little bit?
We'll know.
Okay.
Keep going.
Yeah, we only have 15 minutes. We only have 15 minutes. I'm gonna keep it brief.
Yes, 15 minutes.
But yeah, so we started out a couple of years ago doing conceptual architecture, and this is our competition proposal for the Mastopia competition. I think it was in 2018. And we were lucky enough to win that competition, and this was a shelter on Mars. And we used the reason why it's so hairy is because we used the special conditions of the of the Martian dust to generate static electricity for the habitat. Then we moved on, and we participated in another concept competition for the Moon Village. They had a competition, I think, early 2019 or late 2018, where we did a proposal as well, and we were lucky enough to win that competition as well. And this was for a lunar home that we named the Circadian Lunar Home. And this was the first time that we really investigated the idea of expanding architecture for space architecture. And this was kind of this was at this point, it was super theoretical. Still, we were trying to find as much literature as we could to learn about how this would be possible. But we, after winning these two competitions, we were very focused on wanting to realize our project. We believe that there's an immense power in not just designing about the things, but actually putting them out in real life and learning from that experience. So we were lucky, we were invited to design the extension for a simulation habitat in Israel. It's a Mars simulation mission called Mars, and they needed extra space for their simulation astronauts. And we always start with models. So before we do anything in full scale, we like to work at a smaller scale. And then as we get confidence in the design, in piece of architecture, up in scale and up in complexity. And that's something you will see later on as well. I really hope these videos come through. I'm a little unsure whether or not you'll be able to see this as well as I do. But here we are in the desert of Israel, testing our unfolding skeleton.
We are able to see spurts, Sebastian, but it's okay.
Yeah. There's not that many videos, so I think we'll be fine. I want some time on Lunark, our most recent project. But yeah, after coming back from the desert of Israel, we were super hungry. We had done conceptual work, both in our studies, in the competitions that we had won. We had done a lot of theoretical work, but we really wanted to test the architecture because we had all these subsystems of circadian light panels and algae reactor, all of these things. And after being in the desert of Israel, we really understood how important it was for our work that we tested in real life. And we looked at the kind of state-of-the-art circulation missions around the world, in the desert, and it seemed like there was one big thing that was missing. So there's a couple of analog missions around the world that test that does all the studies under extreme environments, right? And that's super important. We think that's crucial if you really want to study the architecture. If the architecture is a countermeasure for all.
We lost you there for a minute. Can you hear me, Sebastian? We lost you. Can you help?
Yeah, I'm checking on it.
Okay.
Yeah, I think he's completely off. Oh, he's here. He's still here, but I think his internet over there.
One weekend.
Yeah,
all right. So I'm sorry. I'm back now. We are just getting a new internet in my apartment here.
Okay.
So it's everything is we're running on mobile hotspot here. But we really wanted to understand if you're going to test and do psychological studies, understanding social dynamics and all of these things that you really want to understand about astronauts in space, you have to simulate the stressors that the astronauts experience while they are on the mission. There was only a couple of analog missions around was simulating that. And at the same time, we also really wanted to study the architecture, really understand what parts of the architecture could be improved, what worked, what didn't work, how well did it work. And it seemed like in a lot of the other analog missions around the world, the architecture was secondary. There was a lot of things, and it almost seemed like the architecture was an afterthought.
We're not seeing any slides.
Only the desktop.
Are you seeing a slide now?
No, it's the desktop.
Are you seeing a black slide?
No, we are seeing that your computer Windows background, the desktop background with the folders.
Let me try. Here we go. Yeah. Can you see something now?
Yes, we see your screen.
Yes, yeah.
We see the words on the screen. Good.
Yeah. Yeah. So the reason why I showed this picture of the ISS is just this is at this point, this is the state of the art of space architecture, right? This is what the actual space architecture that exists look like. And if you are far away in one of the most hostile environments that humans can imagine. Okay. Yeah. Yeah, I'm here to.
We lost you again, Sebastian.
Yeah, I'm so sorry. I'm just trying one last desperate attempt, and we hope it works.
Okay.
All right. I think it should be a little bit better now. All right. I'm gonna move on a little bit. This is just an image of maybe the most important piece of space architecture that exists right now. The image the cupola on the International Space Station.
That's correct.
Yeah, and I'm going to move past this a little bit. But so space architecture is, you have the opportunity with space architecture to make a completely climate controlled environment. You can make the perfect temperature, the perfect humidity, the perfect light environment. You can basically design everything because it's a completely controlled environment. But we don't think that's the best way to go about this. We think that humans really need variation. Without variation, you start to lose the sense of time. You don't, and people because of Corona now, a lot of people can actually relate. You cannot remember when all the days look the same. You cannot remember when you talked with your mom. Was it 2 days ago? Was it 5 days ago? Was it last week? So you start to lose the sense of time. And at the same time, if everything is monotone, nothing is great, right? A beautiful day is only beautiful because there's a bad day, right? So you need that kind of contrast, and that was also one of the starting points for our habitat in Greenland. So we really tackled two problems, which is also what we generally focus on, and that's the lack of stimulation in space is an issue, and then we wanted to create an expandable structure. An expandable structure, we talked, there was a lot of presentations today about expandable structures, but there was a lot of talk today about expandable structures, but we really wanted to do expandable architecture because of privacy. In the habitat that we were designing was for the near future moon missions, the Artemis missions, where the volume available is extremely small. And that finally brings me to LUNARC. So LUNARC is our moon analog that we did in northern Greenland, where me and my co-founder was the participants in the study for 100 days. 5,500 kilometers from Denmark, far up in the north, above the polar line, all the way up at the edge of the ice cap. And we spent 9 months developing the unfolding origami that makes the habitat. And it was a painful process, and we talked with a lot of experts, both from NASA and around the world, and everybody told us it cannot be done. You cannot make a closed volume expandable origami structure with rigid shells. And we almost believed them, but through prototyping and some flexible seams, we were actually able to do it. And as you can see here, we are moving up into scale, so it becomes larger and larger. And we get more and more confidence with the geometry, the materials, because we also needed, one thing is to make something fold, but you also need to make it fold and be durable in the tough Arctic environment. And here you can see me and my co-founder 16 days before 16 hours, sorry, before departure. We finally wrapped the project. We packed the habitat down, put it in the container, and luckily it fit with just 1 inch on each side of free space. Here you can see me and my co-founder dragging the habitat on the black sand of the northern Greenland at the beginning of the expedition, where the temperatures were mild. Here we are just below freezing. And it was very important for us to create a habitat that could be completely deployed by a crew of 2 without heavy machinery. And here, I really hope this translates well. I'm gonna leave it running for just a couple more frames. Here you can see us over the duration of 10 hours in the Arctic snowy conditions. We are unfolding the habitat. The habitat is made out of carbon fiber, aluminum, and a composite, a flexible seam, and it's super lightweight, and that made it deployable. And we were very satisfied with the expansion. We had more than 750% volume. after expansion. Here's a couple of images of the habitat. So the habitat is designed to be at the peak of eternal light on the south pole of the moon. So the entire facade or the exterior of the habitat is covered in solar panels, these tiny, small, very thin, flexible solar panels. So we could generate energy and utilize the local environment of the south pole of the moon. And at the same time, the north pole also has these very extreme lighting conditions. So for the first 30 days of the expedition, we had sunlight all the time, but for the last 30 days of the expedition, we didn't see the sun go above the horizon once. And here you can see me while we were setting up camp. We had some issues of very strong winds that we had prepared for with these very long earth anchors that had to be hammered down manually into the frozen ground. And of course, that's not an issue on the moon, but at some point we had to develop the habitat to withstand these strong winds and not just the lunar environment. And the entire analog expedition was very true to what a moon expedition would be. We had designed and developed these carbon fiber space helmets that we wore all the time if we were going outside. And the great thing about being in northern Greenland is that it was extremely cold. So that meant that there was no way of cheating. We had to have our spacesuit on at all times after just a few weeks in the Arctic. The temperature was that cold. So it was also, and that's really why we chose the Arctic and northern Greenland. It's in northern Greenland, or you can pick the South Pole or the North Pole, right? But because we are in Denmark and it's closer to the North Pole, we picked the North Pole. But the reason why we picked the North Pole is because you have these interesting lighting conditions that are somewhat similar to what the stressors astronauts would experience on the moon, with long periods of darkness and long periods of sunlight. Then it's extremely cold. So if you go outside, there's not a vacuum, but you can get frostbite, right? So there's that stress, and that's real. So you're very confined. Then it's isolated. So there's, we were far away from anything living, and you need to solve all your problems yourself. And there was a tremendous challenge and a huge amount of stress during the expedition, being that far away from everyone. And then the last thing is you have a very monotone landscape. So you have a landscape without a lot of nature and a lot of life. The only animals that was there was Arctic foxes and the occasional polar bear. We had one polar bear encounter, but luckily it was just a curious polar bear and not a hungry one. So here you can see us on one of our EDAs climbing up one of the nearest mountains in the beginning of the expedition while we still had sunlight. And at this point, we had spent so much time inside the habitat. I think this is after a month, yeah. And we already experienced a lot of muscle atrophy, even though we tried to work out every other day. Inside the habitat, one of the big interior design elements that we wanted to test because of the extreme light conditions, this is a system that we tested for habitat on the moon as well, right? So we created these circadian light panels, and they basically simulate sunlight independently of what the light is outside. So we simulated a lighting environment, a Danish lighting environment, because we are from Denmark, throughout the entire expedition. So we would wake up with sunlight or sunrise, and throughout the day there would be daylight and different intensities and color temperatures of daylight, and then we would have sunset and twilight. And we participated in a lot of studies, our own research projects, but also we were kind of the guinea pigs in a lot of other research groups, external studies, and there was mostly psychological studies and crew dynamics and sleep studies, but one of the biggest, and all that data has been handed in January to all the researchers, and it's being analyzed, and hopefully within the end of the year, all the papers will be published. But but from my own intuitive understanding and what I felt throughout the expedition, the lighting panels was one of the biggest contributors to well-being throughout the expedition. And we did continuous cognitive tests, and we actually performed. There was no difference before the expedition, during the expedition, or after the expedition in cognitive ability, in short-term memory, in reaction time, and all these things. They actually stayed the same throughout, which either proves that me and Carl, we are superhumans, or the architecture worked really well. And I think it's the latter, because we are definitely just civilians. We don't have any astronaut or military or survival training. So here's an image of Carl during one of the more saturated, intense sunsets inside the habitat. So we didn't have any control on the programming of the panels. They were pre-programmed with variation, so the days wouldn't look the same, and that was one of the biggest things. So one day would be a beautiful sunrise, another day would be a boring gray sunrise. It was very small, even though the habitat expanded 750%. The footprint, the livable footprint on the first floor, was only 4.5 square meters. And that's very small. But we had flexible furniture, so we could fold up the tables and use the space to work out, and we used the tall space of the tall volume of the interior to have sleeping pods just beneath the roof. To the left here, you can see an image of taken outside on one of the last days of sunlight throughout the airlock. So the entire habitat was organized completely like a space habitat or a lunar habitat would be organized. So we also had an airlock. In our case, the airlock was great because we wouldn't lose that much heat whenever one of us had to do an EVA. And on the right, you can see an image of the habitat during the dark period. I think this is in the middle of the day, but there's basically no sunlight. We also developed our own entire habitat brain. We have a couple of programmers, data scientists on our team, and they developed the entire technical parts of it. I'm not going to go too much into detail with that, but we named it Odin, and it basically collected data from 72 sensors around the habitat that we are still analyzing now. And here you can see me using the interface, checking the temperatures and of the different sensors, the different spaces inside the habitat throughout the night. That's something we did frequently. And this is the last image taken of the habitat. This is full moon, and for the curious or the cyber detectives out there, you can see out to the right here, I believe it's either dead pixel in the camera because of the freezing cold, or it's a picture of Mars glowing red. So here you can see it's minus, at this point the wind chill is minus 41 degrees Celsius, which is also about minus 41 Fahrenheit. That's where the two overlap, so that's easy to remember. And the wind speeds at this point in the world is incredible. Some days the walls of the habitat would move, kind of breathing. Here's a rendering on the left of what we thought the habitat would look like halfway through development, and on the right is what it actually ended up looking like. And I think it is quite similar. I'm almost at the end, but I just want to show you something of behind the scenes. I think this is something that I wish to see in a lot of other projects, but basically, how is it built? And we built everything from scratch ourselves. There was only, I think it's about 10 welds in the aluminum that we didn't make ourselves because our equipment couldn't handle that amount of energy. So the entire habitat, all the aluminum, we machined it ourselves. The carbon fiber panel, we cut it ourselves and assembled everything with in our workshop in Copenhagen. And we continue today in the same workshop space, doing prototypes and developing our architecture. And here you can see some of our team members assembling the flexible seams and all the different bolts and nuts that pulls this habitat together. And here you can see us using very primitive techniques to lift the top shell up. It was a large piece to manually move around, but because it was made of aluminum and carbon fiber, it was actually not that hard to handle for a group of people. And on the right, you see the entire battery box wrapped in Kapton tape before shipment. And here's an image of the team a couple of days before the final departure. But yeah, so we work with expandable structures, and now we're also getting into 3D printing. We believe that there's a huge opportunity with 3D printing in space. Of course, a lot of people have already worked with 3D printing, especially with the NASA 3D printing challenge. But we want to use it. We want to do it on Earth. So here's a project that we are doing right now. This is our project we started right when we got back, where we are developing together with a real estate developer and a 3D printer manufacturer called Cobot. They make large construction printers in Denmark, printing with concrete. And we are doing 30 houses that are going to be 3D printed this year. And this is not the house. This is just to show you the most recent project they printed with the printer. This is a foundation, 130-ton concrete foundation of a windmill tower. And here's a visualization of the architecture that we are working on right now. And the reason that we are doing that is we believe that there's an opportunity to really mature our design techniques and understanding the process here on Earth before taking it into space. This is our take on developing all these technologies. We need to have a sustainable business model around our entire company, so we can keep doing R&D and keep doing these research projects, but do it in a financially feasible way, and finding projects where we can test parts of space architecture to fund our space architecture R&D is super crucial for us. So that's what I had for you today. I'm so sorry for the spotty internet. I hope that was okay here at the end.
The material made up for that technological problem, Sebastian. I mean, it's a very interesting project. Now, I have two questions. One is, are you both friends after this civil?
Yeah, that's a valid question. When you live next to somebody for such a long time and the wall to the toilet is just 1.5 centimeters, you really learn to know each other too well. But it was actually nice. What we learned was there was conflicts, but we would never go to bed, being not friends. But what happens when you're so reliant on each other for surviving these extreme conditions and extreme environment, you make it work. And it was actually, normally I don't like the sound of a person snoring while I'm trying to fall asleep, but listening to Carl snore in the night was actually a pleasant sound when the alternative was just the storm outside. A little bit sound, a little bit noise from life as well.
Yeah, that was my other question. Did the storms bother you? Because I've heard horror stories about how people behave when these howling storms happen in the South Pole and so on. It's unbearable that you really go wacko. So that is a good point that you make. And we got to run along. Thank you so much, Sebastian, for you to take the time and say hello to Cons for me. and to the rest of your team. We hope to see more of you in the coming few events. Thank you.
Thank you so much.
We are now on to our friend from North Dakota, and Professor Pablo de Leon has created a very unique program there at the university that squarely deals with the humans in space, because he is a spacesuit designer of sorts. We had a hard time picking the picture for you, Pablo, on the flyer, and we decided we're going to put both pictures on there, one with the suit and one with your beautiful smile. Pablo, please go ahead.
Madhu, thank you very much. Thank you for the invitation. Thank you to the AIAA.
You're welcome.
I hope you are all able to hear me, and the screen is being shared with full screen with the presentation.
Very clear.
Okay, great. So I work at the Department of Space Studies at the University of North Dakota. Also very cold, but not as cold as Sebastian, at the place where Sebastian was stationed. And over the years, we built a number of habitats, some of them inflatable and some of them are rigid. And I'm going to briefly cover some of the things that we are doing. After seeing so many impressive concepts of the colleagues presenting before me, I feel a little bit kind of humble, because our project is very, very simple if you compare with so many of the interesting concepts that we saw today. In any case, the name of my presentation is Planetary Habitat Analogs at the University of North Dakota, but we can also call it Why You Shouldn't Let an Engineer Design a Space Habitat Without Supervision. And if you bear with me, I'll tell you a little bit more why I think on this.
Thank you, Pablo. That's a good one.
So as Madhu said, my area of expertise and mainly what we do in the lab is spacesuits. We specialize in planetary spacesuits through different NASA research projects, NASA grants, as opposed to microgravity suits that you will use, for example, in the International Space Stations. These are suits that are specifically developed to have a higher lower torso mobility, so you can actually walk, something that you don't need to do in microgravity. So what we try to research is on the kinematics and the reduced gravity gradients. So that's mainly what we do, and we have been doing through the years a number of prototype spacesuits, some of them more designed for the Mars environment and some others for the lunar environment. And the differences are dust composition, gravity, and a number of other thermal issues that pertain to the lack of atmosphere on the moon versus the lower atmosphere that we have on Mars. So again, this was our area of expertise, and you'll say, what these have to do with habitats? If you think about a spacesuit, and I think it was mentioned before by Phil, the materials of a spacesuit and the materials of an inflatable habitat are very, very similar. So what we did was, in one of the designs of one of our suits, the NDX-2, which is a rear entry suit similar to the Russian Orlans, or the new XEMU that will be used in Artemis, is that they have a rear entry system with what is called a suit port. And I saw that before was mentioned, my friend Mark Cohen, who actually he was the designer and the inventor of the concept of the suit port. This door that is positioned outside of this in the back of the spacesuit, and through a mechanical seal, you can leave the spacecraft or the habitat without introducing dust into the living quarters. So some years ago, we developed a prototype of a spacesuit. And while I was looking at the arm of the NDX-2, I said, well, if we kind of scale up this arm, which is basically a flexible structure, we can have we can build a habitat. So we sent a proposal to NASA, which was called Integrated Strategies for the Human Exploration of the Moon and Mars, that basically had the idea to test three concepts: the spacesuit connected to the pressurized rover, and the pressurized rover connected to the habitat. And then you can disconnect all these three different components and connect them back again. So again, we'll keep the dust outside of the habitat, or that was the idea. We got the grant, and the initial concept was this one, was airtight membrane, the bladder, which hypothetically we're going to pressurize enough so the astronauts could be in a pressurized environment, and then they can build the structure with metal or composite elements and build a floor, the walls, etc., to later put all the equipment inside. So that was the original idea that we had at that time. And also this module was going to be connected through a tunnel that will connect mechanically to the rover, and then disconnect, just like in the airplanes that you remove the gate in order for the airplane to go. So something along those lines. So we started building it. It was work of a couple of years. First the structure, then the covering of the walls, ceiling, all the internal accommodations for the habitat. Again, remember, we have to also design the mechanical driving system to connect with the rover. Inside, it was very, very simple, just a science area, 4 sleeping quarters, very cramped ones, a hygiene area, which is kind of a technical name for the bathroom, a small kitchen, and a meeting area / dining area. So that was our original module. You can see here from a top view of how it was going to be. And here you can see during the first mission that we did, just in one side of the university, to see how everything worked. Once we put the bladder, the membrane on the habitat, plus the pressurized rover, plus the pressurized spacesuits. You can see here a side of the rover where you can see the 2 suits that are connected. I'll show you in another picture how the suits were attached to this suit port system, where releasing a lever, you can detach the suit from the rover, and then you have to walk back and connect back again, which is a maneuver that is kind of difficult to do. And then we started doing a number of analog missions just to test a number of different systems in the habitat, but also to test the spacesuits, to perform different EVAs with different experiments, etc. Now, the inside, it doesn't look like 2001 Space Odyssey or anything like that. It's a very, very, I can say, simple Spartan interior of we're looking at this picture from the kind of the science area, and that day was specifically, everything was very disorganized inside, because there was the beginning of the mission when the crew members are setting everything ready and getting the experiments, getting the food, etc., in the proper places. So, but as you can see inside, it doesn't look anything like some of the concepts that we saw earlier today. This is a very kind of utilitarian, and you can tell that this was, built by an engineer, certainly. So these are just some pictures of living in the habitat. We did missions of up to 30 days so far. You can see, for example, here, this is the tunnel that connects with the rover. So you can, you crawl from the habitat to the rover, you pass through, and then through a remote control system, you detach the gate, we can call it, so you can drive around with the rover, do your extravehicular activity, get back again, drive again to the habitat, and have it connected again. The sleeping quarters are also very, very small, just a tiny bed, and that's pretty much it. But they have a shower, they have a proper kitchen, utensils, etc., etc. So, not happy with the first habitat, we sent another proposal to NASA to build an upgrade of our habitat, consisting in 4 additional modules, and these 4 modules were going to be dedicated modules with specific uses. For example, one was going to be an EVA / workshop module to repair different things and to keep the maintenance and servicing of the spacesuits, and also have the 2 suit ports in the back, in addition to the other 2 spacesuits that remain outside of the habitat in the rover, an exercise and human performance module, biology and geology lab, and a plant production module. So let me just show you some of the characteristics of all these different modules here. They are all interconnected by a connecting tunnel. So you can go from the, without the need of a spacesuit, from the living quarters to any of the other 4 modules. This is just the human exercise with just some simple machines and very basic kind of medical facilities with some telemedicine possibilities in there to transmit information about the health of the crew members to the outside. This is the EVA and maintenance module. Again, as I mentioned before, with 2 spacesuits mounted in the back and some space for repairs and maintenance. And this is the plant's production module that I'm going to talk about in a few moments as well. So we have to build the modules, and the difference between the core, what we call the core module, which is with the living quarters, to the other 4 is that the core module was made inflatable. But here in North Dakota, we have the problem that it's not called North Dakota for nothing. We have very high winds and also temperatures in the winter that goes beyond -50. So the inflatable materials suffer a lot being outside, being constantly battled by the winds, and the habitat was kept in place by full air pressure. So we decided to do the 4 additional modules rigid, so they are made out of aluminum. You can see here some pictures of when we are moving them into the terrain, which in the middle of the summer doesn't look much like Mars, but regardless. Here we are doing the assembly of, for example, these are the trays and the electrical system for the lights for the plant production module. Here you can see some of the different pictures doing some of the analog missions here with some snow, etc. So we have been performing so far 8 missions, 8 analog missions with between 3 and 4 crew members each. We run experiments for different NASA centers so far and universities as well, and some theses for our students as well. So we keep them pretty busy during the time that we do missions during the year. You can see here, for example, in the plant production module, we have some robotic systems to tender the plants, and this was done through an agreement with the University of Hawaii that they develop a 3D printed robotic system that we are using here for hydroponics. So right now we are in every mission with 1% of the food, and again it's a small percent because this was I think presented before by prior speakers, the amount of food that you can supplement the other food that the astronauts will be consuming during the mission. But we have been doing not just hydroponics, but also through a technique that is called vermiculture, using worms to fertilize analog Mars regolith. We have been able to turn a simulant regolith into a fertile place for the plants to grow. So that's one of the other things that we have been doing here, and has been very interesting. We also work with Ray Wheeler as our kind of mentor and great plant genius, giving us great ideas and telling us exactly what kind of lights do we need, et cetera, et cetera. So his help has been really great. What we do there, we grow edible plants only that the crews are able to enjoy, some of them anyways, during the missions. Again, at this point, the percent is very small. So we are carrying with us most of the food during the analog missions, but hopefully in the future we'll be able to increase this number. And we have been also doing some experiments with mushrooms and some other things. So normally we start the plant growth several weeks before the beginning of a mission. So by the time that the crew gets in, because they can't go out other than in spacesuits, they can enjoy the plants in the first few days after they are in the habitat, right? So again, we're testing the two systems: the hydroponically growth versus traditional one, and versus Mars regolith enriched with vermiculture. So these are some pictures of the microbiology and geology module that we are able to perform analysis on the plants. We can also be working with the planetary protection people at JPL to test how some of the microbes grow in the habitat and what kind of issues that can bring in the future to the potential crews. And of course, we do a lot of EVAs. Practically every 2 days, the crew members have to live on simulated EVAs. That again, the landscape is not very convincing, but we're doing the tasks regardless. We also perform a lot of behavioral studies through another university. They develop a portable electroencephalograph that we use inside the spacesuit, so we are able to capture readings of the crew members while they are using the spacesuit, and they are doing very, very interesting studies on that: sleep behavior in isolation, exercise, artificial light as well, and virtual reality training. We are now preparing our mission number 9. There is a patch that is not here, but our next mission, we have to delay it because of the pandemics. But by the end of April, we'll do our new mission that is going to be 21 days for crew members. So right now we are working in the organization for that. You can see here some other experiments of previous crews, and we keep them very, very busy during, we are trying to implement some of the ISS mission planning systems to try to create routines for them, but at the same time, we give them enough time to organize the day by themselves, so they don't feel that they are constantly controlled by someone from outside. So with that, I'm going to finish the presentation. I thank everybody again, Madhu and everybody for listening to this. All right.
Thank you, Pablo, for an excellent presentation. You know, when you practice what we preach, you learn a lot more very, very quickly. And Pablo, I can't thank you enough. Now, the students part of the what do you call it? The simnauts.
Yes. Well, you know, the thing is, the students were involved since the beginning in the planning and the development of the construction of all this was done by students. And also, they are, even if we have people from outside, because in some cases we have people from Johnson Space Center or Kennedy or outside that want to bring some experiments from other universities, etc. We also work with our grad students. Our department is a graduate only, master's and PhD. So the hands-on experience that they have is very well appreciated later by private companies or by NASA or other contractors they will go to work with. So yeah.
Absolutely. And I know you are a very hands-on person yourself. And, tell me, I read that paper that you published with Kavya.
Yes, Kavya Manyapu. Sure. Yes, absolutely. Yes. Yeah. Well, Kavya is now an adjunct professor in the department. So I'm working with her in a number of proposals. So with DUST, She
yes.
developed as part of her dissertation, I think, an excellent system to prevent dust. So we are still working.
Did you get some results from that experiment, Pablo?
Well, we have a sample now in the International Space Station. There is a mission called MISI 11 that is exposure to the space environment, and we took several of the fabric samples treated with this special carbon nanotube system. We're waiting for a Dragon capsule to bring it back to Earth, and we're going to study how the elements of the carbon nanotubes reacted to being more than 1 year in space.
Excellent. Thank you so much, Pablo.
Thank you. It was a pleasure.
Okay, now we are off to our last presenter, and I want to introduce to you Kriss Kennedy, who is not only an architect, but he's one of the first architects I know who worked right there in the middle of the action at NASA, at Johnson Space Center. And he has an accomplished bio with a lot of inventions to it, including the TransHab, which all of us know about. And Kriss now has his own company, and we would love to welcome you, Kriss. Thank you so much for a little bit of delay in getting to your presentation, but glad you're here, and we'd love to hear from you.
Well, thank you, Madhu, and thank you to all of those who are still on at this point. Can you see my slides and hear me okay?
Yes, you're coming through very
well. It's been a very exhilarating day and a glimpse of the future and a lot of really great work. I'm honored to be included among, this distinguished panel of space architects and engineers. As you said, I'm a licensed architect since 1995 and have worked as a space architect at NASA Johnson Space Center for about 30 years. During our first space architecture gathering, I spoke of space architecture at the tipping point. Today, I want to present a vision of United Space Structure's idea of built-in place architectures that I've been working on with them. So what I will present today is a sampling, a high-level overview of our efforts, not by any means detailed design work. So I think Carl Sagan said it best, is if our long-term survival is at stake, we have to basic responsibility to our species to venture to other worlds. And I feel strongly that space architecture will enable humanity to expand to multiple planets. My vision as an architect is to enable humanity to become a multi-planet species. And I envision that the future lunar or Mars landscape of many different and diverse architectures, as you've seen today, much like a city here on Earth has many different architectures. So my question is, what if ISRU-derived structures using automated additive construction was feasible? And we've seen glimpses of that today. When I was designing space inflatable concepts at NASA in the early 80s and or late 80s, early 90s, the fabric technology was not ready for prototyping. We had to wait for stronger fibers and materials such as Kevlar and Vectrans to mature those fibers and fabrics and straps in order to use them and prototype them and test them and TransHab in the 2000 timeframe. So technologies and capabilities are maturing to enable these new innovations in architectures. In situ derived built-in place structures using robotic construction capabilities are being prototyped all over the world. Waterless, using sulfur binders, lunarcrete, as defined by Hussein with the Department of Civil and Environmental Engineering, is one of those types of lunarcrete that I think is going to change how we look and view the future. So our vision is to provide permanent, self-sustaining, Earth-independent structures and habitats, or actually much larger habitats, to enable a robust interplanetary space economy. We will leverage, partner, and utilize services and capabilities such as mining, in situ manufacturing, power generation, and robotic capabilities. We'll become a forcing function. One of our goals is to utilize as much in situ mined and material and manufactured components and products as possible, eventually approaching near 100% as we build our structures. We have defined a number of goals and objectives, but I'm not going to go into all of those today. As anybody who's taken my courses or listened to any of my lectures know the importance of vision, mission, goals, and objectives. So, what is next after the initial Artemis small lunar research labs and habitats that house maybe 4 to 6, 8 different crew members? It's a shift in lunar Mars strategic vision and mindset, a strategic vision of lunar real estate development on a large scale, much like here on Earth in architecture. Commercialization of, we'll have a future trillion-dollar space industry. It will force that function. Will be designed as mixed-use, multi-story facilities for prospective tenants. We'll start with global international building codes and standards as a point of departure in addition to the NASA standards, and will also follow master spec formats. We will adopt and tailor our traditional Architecture Building and Construction Institute master spec specifications, formatting and numbering for our use. We'll force change. I think we need to force a change of how the USA, ITAR restrictions and regulations are forced upon planetary surface architectures. This is not done. We are not using, or we're not making missiles and weapons. We're making surface architectures. ITAR does not regulate the terrestrial architecture industry. So what if then we think about United Space Structure's strategic vision is to build facilities on the surface and within lava tubes using these built-in place structures and robotic construction capabilities. We're planning on using the same patent-pending automated additive construction robotics processes and techniques to build our structures. Our construction robots and processes drive and inform the designs that can be built in place, focusing on simplicity of construction and robustness of the structure. And in my many years as a space architect at NASA, it's always been about the internal architecture for the human health and well-being. So our lunar concrete or lunarcrete approach is based on a paper of performance of waterless concrete, as I mentioned earlier. So my value proposition is this. It's strategic thinking beyond the Artemis initial human exploration. It's about the commercialization and industrialization of space, the moon, and Mars, and moving beyond that. It's about real estate, setting up lunar real estate ventures, analogous to here on Earth, real estate ventures to design, build, and operate commercial office towers and facilities in any city. It's a forcing function of lunar capability and services. We're not going to do all of these types of needs and capabilities and services. We will hire or use and build them, or use other people, their services. And so really it's a forcing function to get these companies focused and start building and thinking about building the types of things that are needed. So it's a market demand and opportunity for in situ manufacturing on the moon. We have looking at various collaboration and partnerships, and there's many technology and architectural engineering opportunities out here. In addition to, we have tentative collaborations with 2 robotic companies and 5 universities. So I'm going to touch a little bit about each of our concepts, and we have other ones, but I'm only highlighting 3 here. So the USS is planning on using the same patent-pending automated additive construction robotics processes and techniques to build our in-place architectures. So we let from the external aspect of it, the architecture looks simplistic. It is not very sexy. But like I said, the focus is on the internal architecture. When I was running the Habitat Demonstration Unit project, our focus was on the internal systems, the operating systems, and getting the technologies working together. That's really the focus of this, is really about the internal aspects, the internal architecture. we would utilize and locate ourselves near in situ resources and settlement strategies. We would use Class 1 pre-integrated habitats, small habitats, as construction shacks during the initial tower construction. Our towers are scalable in architecture, they're customer driven and functionally tailored to each individual intended use and concept of operation. You can see some of the details or some of the characteristics of these structures. One of the unique aspects of this is the internal core of the habitat or the large facility, as we like to say it. And so the other aspect is the actual shell wall construction, in which we are looking at dual use or dual wall design of reinforced tension cables and glass fiber embedded waterless lunar crete with a customized outer shell. And then the shell cavity could be filled with expandable polyethylene foam, high density polyethylene, aerogel, water, or other materials to be determined. We will pre-tension the shell wall reinforcing cables, then overlay a lath and in place the lunar concrete, building up to the required thickness and structural integrity of the pressure cell, given the size and diameter of our facility. This shows some of the internal aspects of it, and a couple things I wanted to point out is what was brought up today, starting with your foundation and using horizontal reinforcing tension cables and glass fibers, but also geopier supports to make sure we have a stable foundation, given the size of our structure that we envision. We also are looking to place horizontal bulkheads. Think of this as a submarine stood on end, where you have bulkheads placed horizontally that can separate segments of the tower should you lose pressure in a certain segment, but also so that the systems can operate independently each of these segments. So if you don't necessarily have the tenants to build out the entire facility, in which case we could make a smaller, shorter diameter or shorter, we can adjust accordingly. We also have been looking at different options on our domes and how to close them out with various glazing opportunities and sunshades. The other thing I wanted to promote is the idea of that we are looking to take advantage of pre-manufactured components, but also to have systems and the ISRU manufacturing start building components for us. And so we become a forcing function again, looking for a service, looking for ISRU companies to build us various aspects of structural components, or even shells, or space frames and components of space frames, or things of that nature. We're looking at a floor-to-floor height that takes into account plenum spaces, utilities, and lunar gravity. We're also looking at aspects of using to make the lunar, from the lunar material, to make glass fibers for fiber optics that could be woven into fabrics for walls and ceilings that could be used in many ways, including the diurnal cycle, to give the different color temperatures. This is a focus a little bit on that core aspect of our vertical shell, the shaft, which could be pre-manufactured and shipped on the first one, but we hope to manufacture those in situ in a manufacturing, ISRU manufacturing facility that would be built on the moon. We're still looking at whether we would have one of these or two or three within each of the large facilities and structures. The other thing is, what it's not showing here is the elevator system, which would be in the middle of that, as well as the utilities that would run vertically. Another one of our designs is a conical tower. So that was a cylindrical concept. This is more of the conical aspect, keeping in mind a pressure vessel. Here again, we can vary the scale, the size, and shape of the conicals to fit the need of our customers. Using some of the same techniques and principles, we would build it similarly, And we would use a construction system and crane system that would then allow us to do 3D printing as we build our shell wall, as well as we're looking at different flooring techniques and flooring systems, and we'll look at different trade-offs as to different ways to do that, whether it's prefabricated or ISRU derived or lunar concrete waffle slab or some other type of flooring system. The other third one is our lunar lava tube tower facility, and actually it was our first concept, which focused on the idea of placing and building a large capability within a lava tube. Now, when you look at lava tubes, and there are 62 known lava tubes on the moon, the unique thing about that is you find that there's skylights or the mouth opening, and that's very difficult because that's kind of the weak spot of the whole lava tube. And so our approach is unique in that we want to drill through the good part of the lava tube down through this, into the cave or the top apex of the lava tube. We have identified 3 possible locations that we'll be sending probes to over the next few years to investigate those lava tubes, and we're working with several universities on different robotic systems that could be placed into the lava tube that will map it and 3D survey it for us. So we plan to utilize these lunar materials and 3D print our materials. As a matter of fact, some of the 3D printing companies that had presented today are some of the ones we're interested in and further conversations with, and the robotic systems to do that. So our idea is the entire facility is robotically constructed. This gives you an overview of that, in which I was talking about how we would drill down through to create a shaft and then lower our system down and build from the floor up using the tension fabric cable system and the lunar concrete, and building as we go up and securing it to the top of the lava tube. And of course, there's a lot of work to do to work out the details of that. As shown in this picture here, we looked again at dividing it up into segments and the different types of concept of operations and different functions and users in these different segments, and it can be racked and stacked in many different ways. But the idea again is creating tower bulkheads to be able to segment off and close off areas should you need to in the future. We've done a little bit of idea looking at master planning. If anyone's seen any of my lectures on zoning and master planning, the idea is to locate your landing pads away from the habitat at least 1 kilometer plus. You can get a little closer if you've got berming around them and sintered landing pads. Typically in the equatorial regions, the flights are coming in from the east and landing and so going the east to west, so your landing pads are a little bit more oval shape. The habitat, or in this case the lava tube, is down at the bottom, in which case we have a rover port at the surface that gives us access to it. We would look at using nuclear power system because we want to create data storage systems and large data capability in the base of the tower. And then you have your ISRU processing plants, manufacturing, and so on. So the one unique aspect of this is the idea of how do you get to the surface if you are living or have this facility in a lava tube. Well, you need to create a shaft that puts then a rover port or an architecture on top of the surface. So it's kind of almost a low impact, minimal footprint as far as on the surface, and then everything else is down below where you have your radiation protection and a constant thermal environment. You also have access to the lava tube in which you can then explore that lava tube cave and continue to build more of these and link them together underground. So it is a unique lava tube architecture and requires these transition spaces between both in the lava tube and to the surface. As I mentioned earlier, we looked at different ways and different occupants within the tower structure. And so we looked at a data center capability, which we have a lot of interest in. Obviously, mining operations to set up teleoperation and mining operations, as well as lunar exploration and research capabilities, food production and processing. A large amount of area would be devoted to that, and recycling, because we want to become independent and self-sufficient. And then you have the crew, human habitability, medical operations, everything up near the top of the tower, close to the surface. We're still doing studies, or will be doing studies, looking at a variety of different aspects of this. The psychology of the internal architecture is paramount for human psychological well-being, and eventually, you know, we want companies to make structural shapes, tubes, trusses, and space frame components, a robotic factory, if you will, that can turn out these ISRU components for us to use and others. So we're really a forcing function of really trying to get an industry stood on its feet and moving forward in a new era of architecture, of planetary architecture. So in summary, what if? What if all this was possible? And really it's a paradigm shift looking toward lunar real estate and development and operations. It's a forcing function to pull technologies and capabilities into service, into being. It's a market-driven approach. So we have plans to prototype a 2-story full diameter structural unit should we get the funding and proceed forward. And use that for testing, use it for evaluations, and maybe even move our offices into it and work out of it. So the lunar and Mars architecture should not fall under ITAR, I don't think. You know, it does it here on Earth. I think it would allow U.S. companies to hire international talent, which is at this point is to struggle for our international space architects and engineers to get jobs in the U.S. working on these great projects. I think change is needed. You know, and there's many collaboration and partnership opportunities here, and we're going to be starting a crowdfunding activity with Net Capital soon. So this is a glimpse of architecture beyond Earth. So these 3 initial patent pending concepts promote simplicity, robustness, and are designed with the construction method in mind. I would like to thank Bill Kemp and James Wolfe, who are co-founders of United Space Structures, and Spencer Stanford, CEO of Precursor Technologies, who's been a part of this team and will be in our future. So we have lots more work to do in the future and ahead of us. So thank you for hanging in there today and listening to my short presentation. Thank you.
Thank you, Chris. Your cadence, your delivery, and the things you said reflect on the practice of the entire profession, and I can't thank you enough. You said a few things that are not only pertinent but are central and core to showing concepts and designs. I put some stuff on chat. Thank you again. Now we have a little time to do a bit of discussion, but before we do that discussion, I want to leave some thoughts in your minds and then go on to discussion. So let me share the screen. Our drop-off rate is pretty high. We started at about 100 participants. We are down to half as many, Chris, but such is life. Let me go here and pull up. Okay, let's see. Conclusion. I want to be sure I have the right conclusion here. I'm going to go pick another one. Give me 1 minute. Okay, what do we have on screen? Ken, Chris, can you see the screen?
No, I only see your folder.
True, I see your folder.
No? Still the folder?
Yeah, you need to share screen.
Okay, hold on. Let me do this. New share. Give me 1 minute. There we go. What do you see now, guys? Still the same screen?
Yeah, still just a folder.
Folder, okay, let me see.
Yeah, you need to click the green button and select.
Yeah, I can't see the green button right now, but I'll get to it. 1 minute.
You have to shrink.
Yeah, that's what I got to do. Okay. What came up now?
No.
Still on folder?
Still folder, yeah. Maybe you have a second screen or something. You need to pull your.
Yeah, let me see what's going. I got the screen here. Sharing has stopped. Okay.
You have to select the slide.
Yeah, let me. Am I on camera now?
Yes.
Okay, hold on just a minute. Okay, what do we have now?
Yes, it's okay.
Good. You know, I'm so glad some of you stuck with us till the end. I just wanted to let you know how some of us think about space and space activities. All of you may know this particular person. If you don't, I would recommend, let me get on the screen here and yep. Is that a full slide now? Ken?
Yes.
Okay, good. So Simon Sinek is an inspirational figure in the corporate world. He goes around saying why we do something is a precursor to how and what you do. It couldn't be true in the space profession and in the space architect's profession. Many of us start because it's a very beautiful thing to do. It's very stylish and so on. But at the end of the day, you think about humanity and how the work we do affects everything. And that is why we think it's important to think about why we do things. Now, on the left corner, you see two of the richest people in the world, Elon Musk and Jeff Bezos. And they both have interesting views. We like to think they are separate and different. But if you reason it down to the ground, they're all talking the same thing. Musk is talking about settling other planets for human survival of species. Bezos wants to protect our Earth from all the wanton industrial rampage and the destroying of our forests and so on. John Marburger, in an address at the Goddard Memorial, which is a cherished lectern for space architects, he talks about going out into space to make the solar system part of our economic sphere. And Joseph Campbell, as you know, the person who enlightened George Lucas with Star Wars, says that many times when these very special people go out and come back, they become enlightened. And astronauts have a different feeling about planet Earth. And so it's about the return of the hero. Freeman Dyson said, we've been looking out into the skies for so long. It's black, nothing is happening, everything is cold and still. Our job perhaps is to beautify the universe in the way we know. And Frank White says the same thing about the overview effect. You go out, look at planet Earth, and you go, my goodness, what a place that we live in. We should take care of it. And finally, in the past few years, a group called For All Moonkind, led by Michelle and Tim, they've been saying that we have to preserve our species heritage wherever we go. I mean, all great civilizations preserve their cultural heritage, and we should preserve our cultural heritage extraterrestrially. So first thing, preserve all the Apollo and other spacecraft that we have put down there on the moon. So these are the ideas that we have been talking about in the school. Of course, we all have a father figure that we look up to, and that is Buckminster Fuller. And when he saw the images come down from the early Apollo missions, everybody started talking about, look at how beautiful the Earth looks from the moon. And Buckminster Fuller, in that year, 1968, before Apollo 11 put Neil and Buzz on the moon, put out a book called Operation Manual for Spaceship Earth. It's a free resource. You must all take a look at how far-reaching his thoughts are in that tiny little book. NASA is already doing some incredible work to make that happen with vehicles. And I happened to tour it while it was at doing their work at DRATS. I remember meeting Chris and Scott and the whole group there working on deep space habitats. Now, you know, if you look at the history literature, you'll come across some very interesting slides. There was a person by the name of Esko von Puttkamer. And there was an office called the Office of Long Range Planning at NASA in the 60s. These are slides from around that time. And I think it was John Mankins who mentioned it to me. Madhu, the way things are going, at the end of the day, when you get things built, they'll still look like somebody mentioned it 40 or 50 years ago. So here we go. When do you think we'll have a manned lunar base? When will we have a manned Mars base? Take a look at it and you'll see we've not changed very much. So what are the things to watch out for currently in the new things that are happening? I think, as I mentioned before, you have to closely watch what is happening in the Earth orbital regime. I think Leo is the next site for action, not only for the number of satellites we are flinging out there, but also for humanity to build large structures. Watch out for SpaceX, Starship Evolution, and the cadence, the rate at which you execute test missions to gain hard data. Lunar missions are getting underway. Parts of Gateway have been assigned. The Artemis project is being thought about and is bound to happen because the new administration has come in full force and said they are going to follow what the previous administration did in a fantastic way. Government-private partnership is something that Chris mentioned. And now NASA has changed their philosophy to one of being a customer, which means what it really means is that some of the intellectual property that belongs in the private sector cannot be accessed by NASA, including reusable rockets. So they need to buy things, and that's a good thing. I think it's welcome. And what will happen in the near future in orbit? I think space tourism, because as you know, commerce and private sector runs on a principle which is very simple, which says that profit equal to cost, revenue minus cost. So that's coming up. So there is a battle between institutional culture, which is 50 or 60 years old for NASA, 70 years old for NASA, and the societal and public inspired desires. What do we want in space? And that is a good balance, because we are going to get there. We are getting there very fast. My own pet peeves, while Kriss was talking, I put them on chat room. You know, whenever I sit in a new discussion, the first thing that is coming up is, hey, what is the impact, the environmental impact in space and extraterrestrial surfaces, which are pristine and have some qualities that we can mess up very, very quickly. Debris is another big problem in orbit. Extraterrestrial habitat, I kept saying, please, 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 space architects, draw foundations, draw dust platforms in your beautiful pictures. You guys do magical jobs. We need more of it. And all of these regular things, micrometeor protection, radiation, thermal, dust, entry, descent, and landing is an area that you need to study. And triple point of water. You will see that there is no water lakes on Mars. Why? Because of triple point of water. You will see there is no ice liquids on the moon. Again, because triple point of water. You need to study that. And guess what? End of December, end of the last administration, a report came out saying that the way to go to Mars is go quickly, and the power source to use for flight and for energy requirements, thermal and so on, is nuclear. So there is a push there. Go to spacearchitect.org, where Kriss and I and Mark and Scott and all of those, Brent Sherwood, have all written so many beautiful documents. Take a look at it. This is my pet peeve. And Kriss said it right. He's nailed it. He said, underground is a place to go. And guess what? Nature has given us lava tubes on Earth to simulate and then execute in extraterrestrial bodies. Can go very fast to Mars. Right now, the consumables for 3 to 6 people, just that alone makes a spacecraft so unwieldy that I don't think we're going to do that. So we need to go very quickly. And 1960s drawing shows you that, because in the 1960s, we built nuclear rockets. It goes, regulation clamped us down very quickly, but we can go very, very fast to Mars. You can wear radiation belts while you're flying, because you may have solar events, coronal mass ejections. And so we are working on nice protection. This is what it used to look like. Guess what? In December, this is how our nuclear rocket ships look like. So we can have 1 week Mars tours, go around, see the planet, and come back. Usually people have 1 or 2 week holidays. They don't have 3 week vacations. Here you go. My own posing. I think Kriss remembers this one. And our own design for a Mars rover. Everybody needs to know what you go to do on Mars. Setting up civilization is great, but it requires a great deal of preparation. Elon thinks he'll be flying 100 ships to Mars before we send people out there. Now, what does it all mean for humanity? You know, there is an institute out there in Sweden that talks about planetary boundaries. We are messing planet Earth up very, very badly. And in my opinion, space activities set an example of how we can have a minimal footprint civilization. Sometimes I think we don't respect nature so much. Of course, the native people say about it all the time, but you know what? We are all astronauts, as the guru says. So the question to all the space architects today is, how does space architecture fit into this whole thing where we want to look after planet Earth and do all the other great things around our solar system and beyond? Look at the UN Sustainable Goals, look at the World Economic Forum. They put out regular ideas and new developments. So I gave you philosophy. We had some visions and architectures today, and some concepts and engineering input. This is what I would say. I agree with T.S. Eliot. And with that, we will now open to discussion for those who are with us. I would love for you all to engage each other. And Ken, shall we open up with the first questions that came up that I recall we had somewhere? Let's take a look.
Yeah.
Can you pull up those questions? Stop share. There you go. Okay.
Oh, can I open Q&A?
Yeah, we are open to Q&A, and we still got a few people here. So let me ask.
Okay.
The first question came from Vitali. I hope you're with us. Vitali, are you here? Yeah, he is. Okay, the question about nuclear, it's the same old question from 50 years ago. How to be safe when you launch a nuclear material into orbit or to another planet? Did somebody else want to say before I start rambling again?
Let me jump in real quick. Yeah, so when I was at NASA and we were contemplating, this was, gosh, in the, like I said, the late 80s, early 90s, we were on the idea that, you know, for some of the facilities, some of the future ones, we needed more power, especially if we were thinking ISRU, because that's going to take a lot of power to do all that activity and the manufacturing. So we were pushing nuclear way back then, and, you know, it came into a lot of discussion, you know, launching it, you know, so on and so forth. But some of the techniques or the stuff that Los Alamos came up with, as well as Glenn Research Center, is it's launched inert for the most part, and you can basically blow it up and it will not contaminate. So there's a lot of work done to, until you activate it, is it hot, so to speak, from a radiation perspective or contamination perspective. So the aspect of a rocket failing and falling into the ocean, then contaminating the ocean, was pretty well dealt with and minimized, at least from what I remember.
That is true. That is what I remember too. Let's go to the next question. It seems to me we need to wait to design lunar until we get some data on life at partial gravity in Leo. Whoa, that's from Jim and Nitz Martin. They are still here. Who wants to answer that? I don't know. You know, my understanding is that the quick way to get partial gravity is to go to the moon. You know, there's a fundamental misinterpretation of what we call artificial gravity. Gravity is not artificial gravity. The thing we call artificial gravity is a centrifugal force that is generated by spinning. It's a simulated force. Gravity pulls you inward. You drop something, it comes back to Mother Earth. Or you drop something on the moon, it comes back to the moon. In a centrifugal case, if you drop something, whoosh, it rushes out and probably litters up the orbital regime. The space station has a bunch of litter following it from lost tools and so on. So I don't think we need to think more about this, Chris.
Yeah, so when I first started at NASA, and I did a lot of research and studies and talked with a lot of the Apollo astronauts. And the ones that were on the surface, their physiological degradation was not as severe as the ones that were left in the command module circling. And so they did see some benefit, actually even of the 1/6 of Earth's gravity on the moon. And we also did research and studies about locomotion and, different 1/6G type of aspects, and even, how that might affect the internal architecture and designing it. But yeah, I tend to agree with you. I think the best thing is really, and we shouldn't be afraid of it. We should be going there. We should be there. We should have never stopped going there. But however, I think our future is waiting for us, and we should not be afraid of the 1/6 gravity. As a matter of fact, I also have a paradigm shift that I think that the systems, the fluid systems, obviously the electrical systems and so on, for use on the moon would not be so different, because there is a partial gravity, than what we're doing here on Earth, and it will not be like ISS hardware. So I challenge us to think a little differently in that regard as well.
Yeah, absolutely right. And to give you a difference between artificial gravity, the simulated gravity, and a real gravity, when you put this big spacecraft that we are testing now, Starship, into a flight profile, it's kind of parabolic trajectory, but when the vehicle is in motion, the acting forces are not just gravity, it's centrifugal forces, and it's messing up liquids inside the vehicle. And hopefully we'll see SN11 fly rectifying that. But that's just a thought. Third question comes, it's a congratulatory note for Vittorio, from Kim. So I won't even ask the question, but you did a great job. Vittorio. Okay. And
thank you very much.
Okay. And one for Jim. Jim Rhoné is right there. Yes. How is your Mars habitat project on Earth? I don't see it anymore in your website. I know why. It's proprietary. Go for it, Jim.
Yeah, sure. No, the reason why it's not, well, we're actually focusing on the biopod development right now, but no, building stations first on Earth and then for Mars is definitely one of our main targets. So no, still up and running, I would say.
Okay, thank you. Is Sebastian still with us? Sebastian, are you here? I don't see him on the screen. So I won't even ask the question. We got to move along.
I don't think he's here.
Okay. So there were two